So if you're in higher level, this topic is for you. We're going to add to simple harmonic motion, and we're going to do the more details here, but they're not actually that hard. I love this meme you'll hear, the frequency of bad physics jokes, it hurts. Sorry, if you're getting really tired of the puns, I'm sorry, because I'm not tired of them. I love these jokes. So let's first talk about simple harmonic motion. Do you remember from the SL topic we learned about this? Right? We learned a little bit how it worked. That we learned that the acceleration was proportional to the displacement. It was negative, of course, because we could say that more acceleration meant more displacement, or the other way around. More displacement means more acceleration, and we can consider that right here, right? If this here is the displacement, here is 0, and over here it's some sort of maximum. Do you remember doing this? I have some other videos showing you this. Then we know that the more we displace this thing to one side, then the more force it feels, so the more acceleration it has. And we talked about how it's opposite in direction, which means if you're displacing it, let's say to the right, then the acceleration is to the left, and if you displace it to the left, the acceleration is to the right. So it's always opposite in direction. But see, now we can actually quantify it. In SL, you said, oh, it's proportional to. I guess we'll never know what the proportionality constant is. In HL, we can absolutely do that. It's nice and easy. It's just A equals, remember, look, we're looking for a minus something x. We're going to have a minus, and we're going to have an x here. It's just that here we're going to put in minus omega squared. So just keep this in mind. This is the official equation you're supposed to use. I just want to help you break it down here. So don't think that this thing is quadratic now or anything. It's still, A is still proportional to x. It's just that the proportionality constant is this omega. It's not W, it's just omega. So let's maybe put in the units here. Acceleration, you know what that's in? It's in meters per second squared. Displacement from equilibrium, that's a distance, so that's in meters. An angular frequency, you have to remember how that works. We have some videos of it in topic 6 actually showing you that. But it's basically in radians per second. Now we have a definition again. This is in your data booklet. You don't have to memorize this. We have omega. That's what this is called here. Omega equals 2 pi over t, and that's actually because it's we talked about it before. That's going all the way around a circle that has a radius r equals 1. So that means the circumference of a circle is 2 pi r. But if you make r1, then it works out. So that's why you have 2 pi r over the time. Remember, because speed is a distance over time. This is where it came from, right? Because you're going around a circle, the distance is 2 pi r over the period, but we made r1, so that just made it 2 pi over t. So this is the equation most people know. However, you may want to use, in fact, pretty much always on exams, they never ask it so easy, they'll always ask you then, oh, what's the frequency? See, that's why we have the frequency here and the Hertz value, because you have to remember this equation, and this is from topic 4, we have it right here, it goes F equals 1 over t. So the frequency is 1 over the period. So do you see how we can almost rewrite our omega as, it looks like a 2 pi times 1 over t. See that? I'm just rewriting it like that. So that means it ends up being omega equals 2 pi times, and 1 over t is f. So this is maybe the other useful one. So you have two different versions, depending on if you're looking at the period of oscillation or if you're looking at the frequency of oscillation. But the key thing is this one right here. A is proportional to negative omega squared x. Well, not proportional, equals. So A is equal to negative omega squared x. Which means if we did a graph of this, by the way, I love the South Park one. He always says, whatever, you're going to have a bad time. Here, as you're going to calculate the angular frequency, you're going to have a rad time. Get it? So let's look at this equation here. We have A equals minus omega squared x. So think about this linearized. If we're going to graph A versus x, we're going to end up with a straight line because, look at this. This right here. Although it looks crazy, this right here is just your proportionality constant. So if this is the y value, this is the x value, then this junk right here is going to be the gradient. Now that means if it's a minus, that means it's a straight line graph that's negative, and it's going to pass through the origin because there's no plus something or n minus anything. That means I can draw it. Maybe I'll draw it in light blue. See if I can do a straight line here. Ooh, I hope it's going to work. Yeah, something like that. Something like this. But don't forget, in this case, so we can go one step further. We can say that the gradient, this is really important, the gradient equals omega squared. So maybe then this will allow you to do it. So if you take a graph, for example, and then you're asked to find the gradient, I've seen them ask you that, especially on paper 2 before. Then what you do is you just take the gradient, you set that equal to omega squared. So that means you could then say, if you really want to go a step further, that means omega then equals the square root of the gradient. Technically it's plus or minus, and we'll just consider the positive part here. So omega is just the square root of the gradient. So that'll actually give you the angular frequency, or the angular velocity, as we say. So this is really, really important here. So let's do an example. I have one from an exam here. So an example that we have an object, it undergoes simple harmonic motion as seen below. Do you notice we have a graph of A and we have a graph of X? What is the frequency of the oscillation? I want to show you a trick though, or a tip, is that whenever you see a graph on an exam, always suspect that the IB is trying to be silly with you and trying to mess around with units. They do it almost half the time. So almost half the time, they're giving you weird units. And this is an example of one. Look, we've got acceleration, which is in meters per second squared. Good. And then we've got X, it's in millimeters. Hold on. That's what I always right away put down like a big thing like this to remind me. Any number I read here, I have to put times 10 to the minus 3 meters, because that's what a millimeter is. So how will I get the frequency of oscillation? What? The only thing I can get from this graph is the gradient, isn't it? And remember we just showed the gradient is equal to omega squared. That's how I'm going to do it. So let's try to find the gradient of this thing here. So to find the gradient, I need to pick 2 random points, and then I need to do rise over run. Isn't that how we often do it? So maybe I'll pick, I need to pick points that pass right through nice things because I'm lazy here. Maybe I'll pick that point there. And I need to find another point that crosses these lines nicely. That way it's not so complicated for me. And actually this one right here looks pretty good. Maybe that one will work. Let's see what we do here. This one right here, let's see. To do a gradient, remember, gradient is equal to delta y over delta x. Now keep in mind this. I'm going to ignore the fact that it's negative. Just because, remember, this really tells me that the gradient is omega squared. Well, you know, the absolute value of the gradient. Technically, it would be this. That would be omega squared. Because you can't square something and get a negative when you're done, right? So that's why, well, unless you do like a negative number inside the square root. But that's weird. So we'll just consider this. Ignore the fact that it's a negative gradient. I mean, the negative tells you the shape. It certainly does. But I think if you just find the value of the gradient, that's going to be omega squared. That's the piece you need to have. Because otherwise you can't take the square root of a negative. You're going to get in trouble, math-wise at least. Unless you're comfortable with complex numbers, but let's keep life simpler. So the gradient is going to be delta y, delta x. So change in y, let's see. Well, the good news is, actually this is pretty easy. I got to go from here. This is, each of these lines is 100. So this is 1, 2, 3, 4. 1, 2, 3. Yes, it's 400. So this will be 2400. It's going to go, of course, down by this, right? Because it goes down to 0. Do you see that? So I can draw sort of a dotted line like this here, and a dotted line like this here. Now I have to figure out this is my delta y. Well, it goes down by 2400 units here. Technically meters per second squared it goes down by. And then in x, let's see, it goes to the right by, this here is at minus 0.5. So it goes to the right by 0.5 then. And I can say that. So of course then this would be in, I got to be very, very careful. Times 10 to the minus 3. Aha! That was a sneaky part right there. I almost got caught by it as well. So I would do this right here on my calculator, right? Whoa, sorry. So I could do 2400, divide that by 0.3, 0.5 times 10 to the minus 3. I end up with a huge number, and that's going to be equal to omega squared. So therefore, omega equals the square root of that number. So I'm going to take the square root of that big number. I end up with 2190.9, let's just say. And of course, this here would be measured in, let's see, radians per second. This is useful. But this doesn't get me my final answer yet. I want the frequency. But remember here we have an equation for this. Omega equals 2 pi over t, or 2 pi f, because f is 1 over t. So because that, I can say then, fine, omega equals 2 pi f. So I'll use that over here. Maybe I'll change the colors here just to change it up a little bit. So omega equals 2 pi f. Therefore, f equals omega over 2 pi. So I'm going to take my answer here, my 2190.9. I'm going to say this answer divided by 2 pi. Put it in brackets to make sure it doesn't think it's divided by 2 and then multiply the answer by pi. I end up with f equals 348.69 something like this. We have to look at how many decimals we can use, but it's usually good enough to just say 350. Let's just say we'll round it to the tens here. And this would be measured in hertz. So this here would be the frequency of this oscillation. So this is actually really fast. Think about it. That's 350 times per second. This is a very fast oscillation, but that's okay. It's allowed to be. So can you see how we can solve this? It looked really tough at first, didn't it? But the thing you can do from one of these graphs, you can get the gradient. And the gradient tells you omega. Well, the gradient equals omega squared. So you take the square root of your gradient. Remember, I took the absolute value of it, though, because technically the gradient was negative. That's true. But I just took the absolute value of the gradient, took the square root of that. That got me omega. And then I set that equal to 2 pi f in order to solve for the frequency. How do we want the period? We could have done the same thing. It would have just been omega is 2 pi over the period. That's it. That's how we can deal with these seemingly really tough questions. For simple harmonic motion, we're going to need some extra equations for this HL business. So remember that when we have something going in simple harmonic motion, we have this x is the displacement. And what's going to happen then is that at some point, maybe over here, it's at its maximum displacement, right? And we're going to actually call that x0. We're going to actually define that here this time. So we're going to have this thing going back and forth again, like it's supposed to. And let's take a look at this equation right here. So we're given that the displacement is x equals x0 sine omega t. And you have different version with cos as well. It depends where you start your timer. Basically, if you start your timer at the end or in the middle, but it's actually not so important. The good news is I haven't seen questions where they literally had you use this exactly like this. They usually have you use things with velocities where the sines and the cosines sort of disappear. So I'll show you a little bit about that in a second. So let's look at this. So we have the actual displacement, which would be in meters. With the maximum displacement, we call it the amplitude, it's also in meters. We have t, which is a time, which is in seconds. And we have the angular frequency, which is in, well, radians per second technically, which is in, 1 over second. So think about the units here. You have seconds times 1 over seconds. Those cancel out, which is good. So you take a sine of something with no units, you get an answer. And you have meters equals meters. Okay, good. The key thing, though, I think, is to know that velocity. How do we deal with that? We know that velocity is normally equal to the change in the position versus time, or change in displacement. So in this case right here, then, if we were to do this, if you remember any math, you don't have to do this derivation. I just think it's a good idea to show you where it came from. It didn't just come from outer space. It actually came from the definition of this. So watch very carefully. That means we're going to take the derivative of this, the first derivative. So to do that, let's see, this looks like a chain rule derivative. That means it's a function within a function. So that means to do this, I would take the derivative of the outside function, which would be x0 cos of omega t. I'd put the original inside, which I did. I'd multiply that by the derivative of the inside with respect to t, which in this case is omega. So that means I end up with, well, I can at least put it down now. I have the final answer. So I have the velocity then is equal to, how should we say it? Should we say x0 omega? I think that's how it looks, isn't it? No, they put the omega first. So omega x0 cos omega t. But you see, I didn't just make it up. It actually came from the definitions here. So that's actually, I think, pretty important here. So this, again, this tells you the velocity of your particle, actually. It tells you how fast it's going at a given time. There's another formulation of it as well that you can see. So they give you another one, which is this one. I think it's more useful because it doesn't have sines or coses in it. So again, this one, remember, it relates the maximum displacement to the actual displacement. So this one here is maybe more useful. So let's talk about how we deal with it here. The kinetic energy. Well, what's the equation for kinetic energy? Do you remember? Ek is equal to half mv squared. But remember what v is. Look, let's go back here. Let's take a v equation. V is omega times square root of x0 squared minus x squared. Omega times x0. Oops. Omega times square root of x0 squared. There we go. Square right here. So that means then if I was to actually do this, I would have 1/2 times m, and then I'd take this omega, this v, which is this, I would square this whole thing. That means I'd end up with omega squared times, and then just I'd have x squared minus x squared here. X0 squared, sorry, minus x squared. This is it. And is this the equation we're given? Yeah. So this is the actual equation for the kinetic energy. So this tells us the kinetic energy at any given time. Well, not time, sorry. Kinetic energy at any given position. So if we know the x value, remember this will be locked. You'll be told like the maximum amplitude is whatever. Then that's this x0. X tells you the amplitude at any given point. So this kinetic energy then is the kinetic energy given a specific displacement value, then you know your kinetic energy at any given time. Now to do the maximum kinetic energy in total, I think it helps to maybe try to draw these things here, or to try to think about these here. So that's why I gave you this little drawing right here. Do you remember we were doing this before? This is in topic 4 at least. Here we have x equals 0, and over here we have x equals max. If that's the case, then remember at x equals 0 we have EP equals 0, the potential energy is 0. But then if we have maximum displacement, then we have maximum potential energy. And in the same way we can talk about V's. V is 0 at the end here because it stops. And because of that we have EK then equals 0 because EK is half mv squared. And over here V equals a maximum, therefore we have EK equals a max. And if we want to graph these, remember we also learned about this. This is displacement. Oh, actually, never mind. I have it right here. So we have this graph right here. So what ends up happening is this then. Depending on your different value of x here, let's see what the maximum kinetic energy is. Maximum kinetic energy in this case, do you notice it will be right here? See this little kinetic energy graph? By the way, that comes from all this, doesn't it? If you think about it, x equals 0, right? The potential is 0. See, that's why I put the little blue one as 0. But at x equals 0, V is maximum, so there it is. And that means EK is max, so in black, that's my EK graph. And this is what I want. I want maximum kinetic energy. So can you see that EK max? Do you see that? It's this value right here. That's my maximum kinetic energy. And when does it happen? Tell me something about it. Do you know what value of x I put in here? Look at this. At maximum kinetic energy, does it make sense to you that x equals 0? Because that's where it's in the middle. Remember, the maximum kinetic energy happens when x is 0. We defined it here. Well, not even defined it. We found it here. So because of that, we know that x has to be 0. So you take your EK equation for anywhere, but for EK max, what do? You take the equation here along the top, but just set x equal to 0. It just disappears. So does that make sense? You just get 1/2 m omega squared x0 squared. Because we didn't have the minus x squared because the x squared was 0. So this is why we end up with this one, which I think, again, pretty awesome. You can actually do this. So see, we're coming up with a lot of the equations. Not all, but a lot of them. And now think about this, the total energy. I mean, at any given point, the total energy, ET, so I like this because these are also kind of working out really nicely. If you understand energy, you're fine here. So the total energy, isn't it just the kinetic plus the potential at any given point? But remember, I could have done this anywhere. I could have done it, in the middle right here, the total energy would be this, because it would be 0 plus this. Over in here, this other extreme, total energy would be this potential, because potential plus kinetic, which is 0. Over here would be this. Basically, we get a straight line here for ET. This is important. Because then, can you notice, you can find the total energy at any given point. But what if we know a specific point where one of them is 0? Doesn't that make it easier? Let's look, for example, when is potential 0? Isn't the potential 0 at x equals 0? If we set x equal to 0 here, we have the potential is 0. Therefore, it's just EK max. So this is why the total energy is equal to EK max. Do you notice that then? See, that's why it's exactly the same equation. You end up with 1/2 m omega squared x0 squared. So I'm just trying to show you where the equations came from. They didn't come from outer space here. They are right there. Whoops. What I'll just say undo that. I'm actually going to put it right here and attempt to do it nicer, like this. Oh, what did I do? I was trying to draw a rectangle. It's always fun to watch someone fiddling with a computer, huh? Not at all. There we go. So this is how we find the total energy. We can say it's equal to the kinetic maximum just because at that point potential is 0. So then it makes it real easy. So that's why that was a little bit convenient. We could have chosen it anywhere, of course, and it would have been EK max plus EP. The problem is then it gets really messy and there's a lot of other terms there. But we can actually just set it equal to EK max, and away we go. So that's how we can find the total energy. So to see how these equations are related, they may look gross, but can you see how they don't just come from outer space? They come from somewhere. Now from simple harmonic motion, we also have a couple of equations here. So we have the pendulum equation, which equates the period, which most people know that, but maybe I'll put it down anyway just to be safe. So T is the period of oscillation, which is measured in seconds. So is this one right here. So maybe we'll just put that down here. And if we have a pendulum that's oscillating back and forth, it has a length L. So that's this length of the pendulum. That's measured in meters. G is the acceleration due to gravity on Earth. So that's in meters per second squared, and that would be 9.81. So this is basically your equation relating the period. Which is kind of interesting. So that means that if you had like a whole bunch of different pendulums of different lengths, and then you were to measure the period, turns out through that and a graph, you could actually determine G, for example, the acceleration due to gravity. In the same way, you have a spring equation. It looks very similar to it, doesn't it? Except the mass here is in kilograms. Spring constant, F equals Kx. That would be in newtons per meter. Because we have an equation F equals Kx, and that's still the same K. So K is F over X. Therefore, has units of newtons per meter. That's how I knew that. And then we have the T is in the period. T is the period in seconds. You might be asked something here. I think it's a good idea just to know that those equations exist in case you need to use them. So if you have a spring, you use this 2 pi m over k. And again, if you had a bunch of data points of mass versus the period, then from there you could actually determine through a graph. Let's say here you graph t squared versus L. Turns out because you have t squared equals 4 pi squared over g. Because I just squared both sides here. So if I did a graph of t squared, t squared versus L, I would end up with a straight line, and the slope would be this. So you can see that right there would be the gradient of this graph. So if we did this graph here, the gradient of it, that would be 4 pi squared over g. In this case here, if I graph t squared versus m, let's see what I would get. Well, because I have t squared equals, let's see, I'm going to square both sides. So that means I have 4 pi squared over k, and I'm going to say that's times m. So in a similar way right here, from there I can determine then, oh, this right here is the gradient. All right, so if I had a graph of t squared versus m in kilograms, then I would expect to get a straight line through the origin, and the slope, or the gradient, would be equal to 4 pi squared over k. Therefore, I could solve for k. Do you see that? If I could get the graph, I could find the slope, or the gradient, sorry. And then from there, I could get k, because I would know that k equals 4 pi squared over the slope. Because I've just rearranged this. So to see how these equations can actually come in and help you out. But I haven't seen them ask very much about them. I think it's a good idea just to know that they exist and how to use them in case you need them. All right, let's do some single slit diffraction. I love this picture about biology to a physics student, just like bird, 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 bird. Because we don't really know anything about birds. Yeah, let's talk about single slits. So here's what happens. When you have light and it passes through one little hole, or one opening, which we call a slit, we're going to define that hole or the opening as B. Okay, can you see that on the drawing right there? So I've got my slit with a little opening B. What happens is this, the light that comes in, it could diffract. Remember we learned that in another topic, that diffraction is the spreading of waves. So light behaves as a wave in this case, because if it was just a particle, you would just see, look at this, see we have a slit here, here we have a screen, and it's a certain distance away here. In this case right here, let's put it, I can define it however I want here. In this case right here, I could define it as a distance r. I can define it as whatever distance I want here. But basically I've got a screen here that I'm going to project the light onto. And if light was just a particle, then you'd expect to see a whole bunch of light right here in the middle, like right where, if you imagine then it's like I pass light through a little opening. Of course you'd expect to see lots of light right there where the opening was. But in certain conditions, if the slit opening is somewhere comparable to the size of the wavelength of the light, then diffraction happens, and that means that wave can spread. So in this case right here, this diffraction, it's going to end up making these weird little peaks here. So what will happen is this. We could define them as, how about I draw them in red maybe. So we'll see like a central maximum, that's true, but then we'll actually see these little other maximums here like this. This is the diffraction pattern for light. And we could actually also talk about this. Look, we can have, if we define some central place right here, this would be the central peak here. Then we could define, angles. We could define angles anywhere we like, right? We can put our angle wherever we want. So we can basically be looking at, what's that angle as we go along here. Now, the reason why we can do this is because, can you imagine now, imagine this piece right here where I've got all the light right here. So you see like where all the light's being projected here? That's right here. Imagine that thing then, look, watch me. Imagine that thing is actually turned to its side, and then we were to plot the intensity. Can you see this right here? Then this would give me this. Keep in mind my angle is not going to be in degrees, it's in radians. It's really important. And then we can draw what's called the diffraction pattern for this. So I'll draw it maybe in light blue right here. It should go something like that, and then I'll go back up again. This is at least the first maximum, I guess. I'm just trying to draw it nicely here. Of course, this would be you see this is the peak plus the darkest spot plus the next peak. Can you see that? I've got, basically what I've just drawn is essentially I've drawn this. That's become over there. You see that? That's sort of what I've tried to draw here. So this right here is what I've just drawn. Let's see if this actually makes any sense to you. So the important thing is that I've taken this right here then and I've sort of projected it like this here. So now on the x-axis is radians, and this is the brightness of the light, the intensity of the light. This is the diffraction pattern for a single slit. This is what it looks like. So we have an equation that you're given. So the good news is we can quantify this. We say that theta is equal to lambda over b. This will tell you at what angle do you get the first minimum. In other words, that value of theta that we just found, that tells you this one, right? That's this right here. This right here, theta right here, this sort of along the x-axis here, this is theta in radians. It tells you where you find the first minimum. It's right here. So maybe we're asked for like, what's the width of the central maximum? Then it would be twice that, if that makes any sense. But now here's the problem. This is an angle. And on IB questions, you're almost always asked not just for the angle, but to actually give a real distance. If you imagine this, look, you have an angle that goes out like this. Does it make sense to you that if you have a small angle, or well, no matter what the angle, if you don't go very far out, you have a small distance. But if you go really far out, let's say like a kilometer out, maybe you go like a kilometer up or something. So see that actual distance projects because of the angle. And you might think, oh, do I have to use cosine or sine or tangent? You don't, because these angles are pretty small. Actually, no, even some of them are pretty big. It doesn't really matter. But we can use this thing, because the angle is in radians. This is a really nice trick to remember. If you're taking mathematics, this is the arc sine. This is the length, sorry, not arc sine. This is the length of an arc. So this right here, if the angle is in radians, only if the angle is in radians, this is the radius here of a circle, then this length right here, that will be the arc length. In this case here, we can say that, if it's a small angle, arc length is pretty much straight. This L is pretty much straight. So then we can get the real distance. It goes L equals R theta. That's how we can project this to a real distance. So let's do a real example just to make sure it makes more sense to you. So here we go. We have light and it passes through a single slit. It's projected onto a screen that is 3.5 meters away. So again, that means we have this sort of thing right here like this. And we have this distance right here is 3.5 meters. Now the wavelength of light used is 633 nanometers. So I hope you're okay with that. That's lambda, 633. And nanometers means 10 to the minus 9 meters. If you don't remember that, you can always look it up. The very first couple of pages on your data booklet tells you these conversions. Now the slit is 0.59 centimeters wide. What does that mean? Look over here. That's B. B is the slit width. Oh, by the way, I forgot to tell you, this right here, the angle is in radians. I forgot to define these here. Wavelength is the lambda, that's in meters, and the slit width is also in meters. So notice we have an angle which is in radians, has meters over meters, so that's where the units cancel out. That's good. So here I am. I've got this value right here of B, which I know that B is 0.59 centimeters. Now let's be very careful with this. B, careful. Let's write B is 0.59, but a centimeter is times 10 to the minus 2 meters, isn't it? So just so you know, it's really important that you put in the proper units for this. So now we got everything in meters and meters, so now we're ready for it. So we want the width of the central maximum. Well, do you remember that if we do this whole thing right here, this is the intensity graph. The central maximum that we're looking for is actually this right here. We want this whole thing right here. But we know that equation right here, this theta equals lambda over b, that's for the first minimum. That's the angle to get to the first minimum. So that's going to be helpful. So let's try to find actually that angle. We'll see if we can find just this little angle right here. We can find that angle theta, because theta is lambda over b, which is 633 times 10 to the minus 9 meters over b, which is 0.59 times 10 to the minus 2 meters. I use my trusty calculator. Whoa, excuse me. I do 633 times 10 to the minus 9, divide that by 0.59 times 10 to the minus 2. I am left with an answer of theta equals 1.07 times 10 to the minus 4 meters. Now, we have to be very, very careful. This right here is this angle right here. Of course, then what I could do is I could find that length then, if I want to project that. Remember, I can use this arc length formula. I showed it to you here. This one right here, we have L equals R theta if it goes like this. So let's draw it like that. So we'll have this right here. This is R, and we'll say R equals 3.5 meters. I want this L value, which I don't know, and this right here is the angle theta. So I know that L equals R theta, which is going to be equal to 3.5 meters times this angle right here. Oh, wait, watch out. This angle is not in meters. I hope you were screaming at me for that one. The angle's not in meters, it's in radians. Silly me. So I'll put it down. There we go. So we have 3.5 meters times some radians. Whoops. There we go. So times this number here, 1.07 times 10 to the minus 4. Let's see what we get here. This is the length here, so I'm going to just take my answer from my calculator without rounding and keep the extra thing. So I get 3.75, let's say, times 10 to the minus 4 meters. Now here's the thing. This distance right here that I found, that's only the distance right here. I've just found this. If I want the width of the central maximum, okay, I have to double that. I don't know if that makes any sense to you. So the width of the central maximum, this is really important. Okay, it'll just be equal to 2 times this 3.75 times 10 to the minus 4 meters. So I'll just do that times 2 on my calculator, and I end up with an answer of 7. Now let's see how many decimals I can use. I can only use 2 significant figures, so I'll say 7.5 times 10 to the minus 4 meters, which is very small. Well, that's okay. It should make sense, right? This is a very, very small thing here. This is 7.5 times 10 to the minus 4 meters. Or you could say it's 0.7 millimeters, you could say, right? I mean, there's a lot of ways of determining it, but there you go. This is how you can use this single slit diffraction equation here to solve a real life question. So multiple slit and thin film interference. I like this one. Diffraction gratings are so groovy. I've also seen like diffraction grate things, like G-R-E-A-T, grate. But let's talk about this. So we have a multiple slit interference. What does that mean? Here it's you have what's called a diffraction grating, which means you have a whole bunch of different openings for the light to pass through. And because of that, we could define this D right here. That could be the slit separation, we could say. So maybe we'll just put it right here. So we'll say the slit separation. Maybe I'll put that down right here. So I'll say D. We'll say that's the slit separation. And that'll be measured in, I hope you agree, meters. And then we're going to have, of course, lambda is the wavelength of light. That's measured in meters as well. We're going to have n, which is going to be the order. So this, in this case here, n can be, it's like a running number. It can be n equals 0 or 1 or 2 or 3, ... something like this. That's how it'll work. And then theta will be this angle right here that we've drawn here. So if we try to do this, the way it would work then is you could set, this is actually, the reason why you have this is because, do you remember from topic 4 before, we have constructive interference. If the path difference between, two different beams of light in this case is equal to n lambda, so some multiple of lambda. That's where this n lambda came from. That's because it's constructive interference. So this tells you basically where your peaks will be. And if you actually want to draw the peaks themselves, your intensity, it'll go like this. It'll be like, you know, sort of these really sharp little peaks like this here. It'll just sort of repeat like this, like that, something like this. This here will be your peaks. I think that's about all you really need. So let's just take a look and see if we can do the next equation, which is with thin film interference. And then we'll see an example. So here, if we have a thin film, what we have is we have a thin film. We'll say the thickness of it, we'll call it D. So that will be measured, of course, in meters. I love this one does not simply understand IBHL physics. That's from Lord of the Rings, right? This guy always dies in movies, doesn't he? Or shows. Like in Game of Thrones. He in the very first season, right? But anyway, so we have an N. This gets a little bit confusing because in the past we've often been using these order, so we can say like 0, 1, 2, 3. N has always been this order. Here, however, they've got M being the order, where N here is the index of refraction. So just watch out for that. That's the difference between N and M. This N changes; it becomes the index of refraction of this light, not this light, this material, whatever it's passing through this thin film here. So M can be 0, 1, 2, 3, 4, whatever numbers you want. And lambda is the wavelength of light, which is measured in meters. And index of refraction has no units. So we end up with this equation right here, that we have constructive interference. We say if 2dn equals m plus a half lambda. Now we also have destructive interference if 2dn equals m lambda. Basically, you just have to look at what it is that they're giving you and you can figure this out. What's really going on is we have light, like one beam of light here, one ray of light. It's coming in and it's reflecting directly off that surface, this thin film. So it reflects directly off, there you go. It's received somewhere over here. We have some of that light, however, will go through that into this material here, into this thin film. And of course, it will refract. So maybe, for example, if this thin film had a higher index of refraction than air did, then it'll do something like this, right? It'll slow down. So that means, remember, we learned about this in topic 4. The angle here in is, this angle here is smaller than that one. I guess it slows down. And now we could say, great, it does that, then it bounces off, and then it does the same thing, except now it refracts in the other way around. So here, if you look, the angle is very small, now it becomes bigger. And these things end up hitting parallel like this. So you can basically talk about where you're going to have peaks, which is constructive interference, and where you have dark spots, which is destructive interference. Actually, that's about all you need, the theory you really need for it. Let's see now if we can deal with a couple of questions here. First of all, what will be the shape of the interference pattern that's formed by monochromatic? Remember, that just means wavelength equals just one number. Light that's passing through a double slit. Well, what happens is if you have a double slit, what we can do is we can maybe try to draw the interference pattern here. What will happen is this: you're going to have a single slit thing right here that's going to modulate this double slit thing. So you have basically multiple slit interference. Remember that, that wants to do this sort of shape, but it's going to be modulated by this single slit thing. So remember the shape of a single slit diffraction did something like this, like that. So what you're going to end up having, it's going to look kind of weird, but watch this carefully here. You're going to end up having, if this is in the center, I guess. Let's do it like this. So here can be theta, this could be the intensity. We could say it's going to look like, watch very because it's going to be kind of cool here. So you're going to see it go kind of up like this right here, and then this thing is going to go down like this. I'm drawing a dotted line for a reason. Because what's going to happen is you want to have this kind of shape, but you also want to have this kind of shape. So what you're going to do, you're going to have all these little squiggles like this, but they're going to be sort of bound by this thing. That's what I mean by modulated by. So now it's time to have a little bit of fun here and try to draw maybe a different color. I'm going to try to draw some little squiggles that have to fit within this. I'm just going to just start to draw squiggles here. It doesn't have to be exact, but something like, this right here. I'm going to go up and down, like really high things right here. Probably have a peak right in the middle. This. No, it doesn't make that sound. Basically, if you get the idea here, this is something here that's this kind of shape right here. Looks a little bit complicated, but you have to just think it's going to be a regular multiple slit diffraction thing that's modulated by a single slit. So this is the shape of it. I think it's kind of interesting. Then we have a real question here. Parallel beam of monochromatic light. That means we can find lambda. Hey, that's the whole point of it. We're supposed to find lambda. And it's incident on a diffraction grating. So that means we have this situation like before. We have a whole bunch of different holes here. we need to find this d, I guess, right? We're going to need to know that, diffraction grating. We know there's 600 lines per millimeter. Now the light's initially normal to the grating, which means it's, this way here like this. That's the way the light is. And second order maximum is seen at an angle of this much to the normal. So what this means then is we have a second order maximum, which in this case right here, let's see, well, let's look at the equation first. Maybe that'll help us. This equation here, n lambda equals d sine theta. We're going to need that. Okay, so n lambda equals d sine theta. Try to remember that. Here we go. We'll use n lambda equals d sine theta. N then will be if it's second order, that means n equals 2. So you're okay with that? That means then I can put in a 2 here. So 2 lambda equals d sine, and then theta is my angle that, where I see the maximum. So in this case right here, it's going to be 43 degrees. And I need to solve for lambda, so that's going to be pretty easy, right? So lambda is going to be d sine of 43 degrees, all that divided by 2. Pretty easy. I just need to find d. See, that sort of tells me my mission then is I need to find out what's d in order to find lambda. So how will I get d? I need this distance right here. But they've told us a bit of information here. Look carefully. They said there's 600 lines per millimeter. What does that mean? That means there are 600 lines like this per millimeter. I'm going to try to convert that to meters first. I need things in meters. So I'm going to try to get something that cancels out the millimeters. So I'll put millimeters on the top. I'll put meters on the bottom. So do I know how many millimeters are in a meter? I do. There's 1,000. There's 1,000 millimeters in 1 meter. So that means the millimeters cancel out. So now I have 600,000 lines in 1 meter. This is going to be useful because some people, we can actually call this capital N. That's one way to do it. But D is always 1 over N. So this is actually maybe an important thing you might want to know about. I don't think you have to necessarily memorize it. If you look carefully at the units for it, it should work out. So let me show you something here. The reason why is because I need to know this D in meters. Do you notice here I have 600,000 lines every meter? I want how many meters per line is it? So if that makes any sense, I want to do 1 over this answer. So that's why this D equals 1 over N sort of came from that. It just says, well, all I could do is I know the 600 lines per millimeter. I fixed that to meters. But I have to do 1 over that. That'll get me meters per line. And I needed it in meters, didn't I? I needed a D in meters. That's why I do 1 over 600,000. Oops, too many zeros. I end up with an answer of D equals, hopefully you're following with me here. I end up with that D equals 1.66 repeating, obviously. So I'll say 1.67 times 10 to the minus 6 meters, which should make sense. If you have 600,000 lines in 1 meter, it should make sense you have not many meters for 1 line, right? It should be a very, very small number. So I plug that into here. So I end up with, maybe I'll do it in a different color. Therefore I get lambda equals D, which is 1.67 times 10 to the minus 6 meters, times a sine of 43. And I may need to make sure that's in degree mode, so make sure my calculator is in degree mode and divide that by 2. So I'm going to check my mode on my calculator and make sure I'm in degrees, which I am. So I'll do sine of 43. That times 1.67 times 10 to the minus 6. I get that answer, and I take that divided by 2. I end up with a wavelength is 569 times 10 to the minus 7 meters. You could say that. That could be your answer. Oops, 0.69. How many decimals am I allowed? I guess I'm allowed 3 significant figures, so I can say that. This is fine. However, maybe I want this in nanometers just to sort of compare. So if you look at this, I move this over by 2, and that'll make it 10 to the minus 9. So I can say it's 569 nanometers. There's my final answer. Not too bad, huh? Now it's time for resolution, which is actually one of my favorite things you learn in IB physics. So I'm glad you get to do it in HL. So I want to explain this. It's actually called the Rayleigh criterion, or I don't know how you say it. Do you say Rayleigh? Rayleigh? Either way, this criterion. We're going to talk about what it means to be just resolved. And I think it's really important to remember again, what does the interference pattern look like for one object? Remember, if we had like one slit and we had light passing through it, the diffraction pattern would look something like this. We say the interference pattern, sorry, something like this right here. Well, I didn't draw it very nicely, but something like this, with little peaks like this. This would be one object would do this. Here's the situation. Watch me here. What if you have two different objects? Now those two objects then, you know, a lot of the examples are like, you know, at some distance away, like way, way, way far away, they're going to appear like one object. And then as, you know, they get closer, then all of a sudden you can tell them apart. You can distinguish them. You know, the example could be like, you know, you're driving at night and there's a car and it looks like one light. And at some point you can distinguish, oh, it's two headlights. And now you know it's a car. So when does it happen? Going from sort of one to two things? That's what we call just resolved. So this is when this happens. So imagine now you have two different objects. Each of them is going to make this sort of diffraction pattern, like on the screen right here where I'm pointing. You see that there? So it's going to be two different diffraction patterns that are going to look just like this. The issue is we're going to have an angle between them. So can you imagine that I can make one diffraction pattern? Actually, here, what I'm going to try to do, let's see if I can do this here. I'm going to try to make a one diffraction pattern here. Oh, I hope I can draw this okay. Like that. And it keeps going like this. I don't know, something like this at least. This is, I think it's good enough. So let's attempt to, let's just see now, can I actually copy both of these? No, maybe I'll just try to envelop both of these. Okay, good. So I'm going to try to copy this, and now I'm going to try to paste this. There we go. So imagine that I took this thing right here. Oh, can I change its color? Oh, even better. I'll change it to maybe purple. Nah, red. So here's the issue. Imagine this. Now I've got two different objects, and this is going to be really clear how they go on this. Like watch. So I got two different objects. Can you see how here the two different patterns, they're really far away? See, like, I mean, we're literally going to look at the distance between their peaks here. Remember though that x-axis, that's radians though. Remember that. So what happens is this, as they get closer and closer together, I can't tell them apart. You know, then I can't distinguish them. When they're really far away, I can totally tell them apart. What happens when you're just resolved? Watch this. It's when I'm going to place the peak of one on the minimum of the other. So it's actually going to be right. If I've done it right, it should be right here. Why is this? This is because, take a look right here. I'm going to draw a little dot line. See the peak of this one right here, of this red one right here? Watch, this peak right here lines up with the minimum of that one. And this peak of this one lines up with the minimum of that one. So we would say that, see this angle between them here? This is an angle in radians, if that's the angle between the peaks here. I mean, it looks like an x-axis, but it's actually an angle, and it's in radians. So this is the interesting part here. We have this equation right here that's going to tell us this. And you don't have to memorize this one, you can look it up. But it says that theta equals 1.22 lambda over b. That's the Rayleigh criterion. That's how you know two objects are just resolved. This works for a circular aperture only. So that means if the entrance, the aperture, the hole the light's passing through is a circle. That could work, for example, for your eyeballs. I've seen questions on exams that talk about your eye. They talk about the aperture there. It could be a telescope. They like to do that because that has a circular aperture as well. So we're going to define the angle between those two interference patterns. See that theta right here that I just drew? And that'll be done in radians, so rad. Then we got the wavelength of light, that's in meters as usual, and this aperture width, that'll be the size of the opening, that'll be in meters. So this is the key thing is this, we say they're just resolved if this happens. So the key thing then, the stipulation is this, what if the angle is less than this? You know, if those two things are closer together, then you can't tell them apart. And if that angle is greater than that, then you can tell them apart. And right when it's equal to this magic number, that's when we say it's just resolved. So this is this term resolution, which you use a lot for your phones, don't you? And for screens and things like that. They always talk about the resolution. How many pixels per whatever. This is the resolution. This is related to this exactly. This is exactly how can your eyes tell the difference between, you know, different pixels. Can you see it? What can you image maybe from space? These kind of questions. Those are really important. But now, again, this tells you the angle between two things, but often you want the actual length, like the physical, you know, length in meters. So how do you project this? We've shown this a few times. Remember the arc length formula from mathematics. It says that if your angle is in radians, and this is the radius of a circle, and this is the arc length formula here, then it says that you can just say that L equals R theta if your angle is in radians. Super easy. So that's the one we're going to use. Now let's use a real example. And this is actually a really neat example here. So what if we have a spy satellite and it's orbiting at an altitude of this? Now I've done a little bit of dodgy stuff right here with this example just to linearize it, but it's going to get you pretty close to what you're actually looking at here. So this is the interesting part about this question here, is that like the US military, for example, they use these spy satellites, and some of them, for example, are called KH-11s. And these ones right here, we know that their diameter is 2.4 meters because we can tell by the kind of rockets that they actually use to launch them. Also because the Hubble Space Telescope is very similar to a KH-11, just looking up at the sky instead of looking down and spying on people. So we actually know the size of that opening. So we know the size of the opening is, we know that B is 2.4 meters. Now, we want to image at wavelength of 550 nanometers, so now we know lambda is 550 times 10 to the minus 9 meters. And we're going to say that it's orbiting at an altitude of 250 kilometers. Now, this part is a little bit dodgier because I've had to linearize this. Not linearize, sorry, circularize. In other words, real orbits of satellites are actually elliptical, so they do change their altitudes. I've just made it a circle to make it a little bit easier for us. So this is fudging the data a little bit, but not by much. You'll see this actually gets us very, very close to what's, well, the US military won't tell us this, but this is what it is. So this height right here is 250,000 meters, you could say, right? Because it's 250 kilometers. Here we go. And what we want to do, minimum resolution, what that means is that we need to take this right here and try to find out, like, what's this length right here. If we use this arc length formula, where this is theta, then we want L. This is what we're looking for. We want this distance right here. Like, what's that distance it can actually image? We're going to call this the diffraction limited, because this is as good as it could possibly be. In real life, it's going to be a lot worse than this, because there's going to be things like the atmosphere itself is going to mess up the image, because it's going to make it fuzzier, because the wave fronts are not uniform when they reach you. They're all messed up. That's why we take big telescope like the Hubble Space Telescope is out in outer space, so that it can image things better, so it sort of untwinkles the stars. Although now we have telescopes with these big adaptive optic systems where they basically bore-sighted a big, giant, ridiculous laser. And that laser actually excites some atoms high in the altitude. What they can do then is sample those and actually use that to untwinkle the star by having a movable, deformable mirror. It's actually kind of magic. But let's just look at a spy satellite here, what it's doing. So if we want to do this minimum resolution, remember, we've got to apply this Rayleigh criteria here. Theta is 1.22 lambda over b. So let's figure that out. Okay, so we're going to put that in. So theta is 1.22 lambda over b. Always write this for your examiner so you can show them you know what you're doing. Then we're going to put in the wavelength, which is 550 times 10 to the minus 9 meters. Divide that by b, which is 2.4 meters. I'm going to use my calculator for this. So 550 times 10 to the minus 9, multiply that by 1.22, and divide that by 2.4. I end up with an answer of, boy, that's really small. I guess it should be. It's a spy satellite after all. It's pretty good. This is not degrees. Remember, this is radians. This is my angle. So that means this, I know this angle now. And remember how if I want, I have that angle, now I just have to project it over distance here and find out, what that gives you when you actually look at the distance. And that's when I can use this L equals R theta equation, because I can say that L equals R. R is this value right here. If this was a whole circle going all the way around, then R would be 250,000. And theta would be that answer we just got here, 2.79 times 10 to the minus 7 radians. That's a dot, by the way, not 2 point. So I'm going to take my answer basically on my calculator and do times 250,000. I end up with L equals 0.0. I should probably just do this to, I could say, well, 6989. That actually rounds to like 0.07 meters. So think about this. That's 7 centimeters, roughly. So what this tells you is that from space, in theory, this KH-11 satellite should be able to image up to, 7 centimeters. What that means is that it can distinguish anything that's bigger than 7 centimeters. It should, in theory, be able to distinguish them, which means, I don't know, what if you're going to give that satellite the finger? Let's say you gave it the middle finger. As long as that's about 7 centimeters, in theory, I guess, they could see your middle finger there. If you're a conspiracy theorist, you might be worried about that. I don't know who they are. There's no nefarious intent, really. Well, I guess there could be, especially depending on where you live. But can you imagine that you could actually, in theory, then sort of give them the middle finger, and if they could image at 7 centimeters, I guess they could probably, maybe, possibly see your middle finger. They could actually tell it was a middle finger. However, it's a lot worse than that. So that's, like I said, that's the maximum. That's the best you could do. Of course, you could try changing the wavelength. You could try changing the aperture, and this is what we do. So, but if you want to take, optical images, this is what it looks like. You could, by the way, reverse this. What if you set this to be, what if you wonder, how big of a telescope would you need to, I don't know, see your fingerprints from space, for example? There's a Reddit forum, there's a Reddit thread actually that's all about conspiracy theories. I really love reading that one, and I have to admit I'm a bit of a troll. I sort of go in there and sort of get people really excited sometimes just because I enjoy it. I don't know why. I get a sick pleasure from that. But for example, something like this, people would freak right out about this. Like, no, you can do the math and figure it out. You can figure out what you would need. So in optical situations like this, you could figure out what's the value of B. So in other words, you set basically your resolution equal to roughly your fingerprint. So I don't know, maybe like a millimeter or so. Put in a millimeter here, so like 0.001 for L, and work your way backwards and solve for B. And you'll find out what size of a telescope you need in theory to take your fingerprints from space. So until they start making telescopes that wide, you'll see it's really wide. You don't have to worry. No one can take your fingerprints from space yet. They can do a lot of other weird things from space, but not that, not yet at least. Isn't that cool? Now it's time to look at the resolution or the resolvance of a diffraction grating. Now, like this from Dwight Schrute here from The Office, wrong size does not depend on the pixel. It depends on screen resolution, screen size, and pixel size. It's all about resolution, right? So let's talk about this. Resolution itself of a diffraction grating. Remember, that's something where there's a whole bunch of slits for light to pass through. We had this diffraction grating equation before. We can now look at how well it can resolve here. We're going to call this thing the resolvance. This idea here, we're going to call it resolvance. It's just this term. Now, what we're going to do then is take a look at this and see what we can do with it. We have this equation here. It's given in your data booklet. So let's just maybe take a look at each of the pieces here, and we'll see how we can figure it out here. Lambda is the wavelength being investigated, so that would be in meters. Then we've got a delta lambda, which is the smallest possible resolvable wavelength difference. In fact, this is often the key thing you want to find here. This is the difference in wavelengths that you can actually tell apart. Now we have this thing called diffraction order. Remember, that could be, m equals, 0, 1, 2, 3, ... right? You can have anything. And n is just the total number of slits being illuminated. So this is just it's just a number being illuminated. So let's say you have like 50 slits being illuminated. Fine, n is 50. Do you notice, by the way, that m and n, they don't have any units? So that's why the unit of r, then, there's no units for it. You see that? You can also see it here. You have wavelength, which is in meters, divided by another wavelength, which is also in meters. Meters over meters, no units needed. So although this equation, maybe it sounds a little bit scary, that the resolution of a diffraction grating, oh God, what do I do? Just calm down and look at this equation, and you'll be fine. Let me show you an example. You'll see how this is the kind of thing that they ask you on an IB exam here. So we have a beam of light at different wavelengths here. Okay, so this is not monochromatic. It's, lots of different wavelengths here. It's incident on a diffraction grating with 600 lines per millimeter, and that diffraction grating is 20 millimeters wide. We'll see what to do about that in a second. We have the average wavelength of the beam is 620 nanometers, so we're going to use that for lambda, by the way. That's times 10 to the minus 9, right? That's a nanometer, as I remember them. Calculate the least difference in wavelength that can be resolved by this in the second order. What does second order mean? Let's just go back. Actually, let's just write down this equation. Or, can I be clever? And copy it. Let's see if this works. Copying and pasting is my friend. Yes. So let's just use this equation here. We don't really need the resolvance itself. Do you notice? We don't really need to find R. They could have asked what's the resolvance. Fine. It's this over this. Do you notice here, though, what we really need to do, we're going to work on, let's just work on this right here. So instead of R, we don't really care about what R is. We have this equation right here, right? Mn. We want the smallest difference in wavelength. That's this delta lambda. So if I just rearrange, then I have delta lambda. Let's see, I put this up at the top. That means the Mn can come down at the bottom. So it's going to be lambda over Mn. This is what I'm going to need to do. I know my wavelength. It's 620 times 10 to the minus 9 meters. So that's nice. I know my order is 2, so I have 2 times n. Here's the problem. What's n? Uh-oh. I need this. I need to know, remember what this is? N is the number of slits being illuminated. So let's look at carefully what they gave us here. We have a diffraction grating. Let's see now, we have 600 lines. I'm going to actually just put the units like this, lines per millimeter. You could convert this to meters, but watch carefully. I don't think you have to. If you know it's this wide, can you see that if I multiplied by this number 20 millimeters, do you notice what would happen? I would end up canceling out the millimeters and getting an answer of lines, which is what I wanted for n in the first place. So that's why I can say 6 times 2, which is 12, and then add 1, 2, 3 zeros to it. So I know that n equals 12,000. I have 12,000 lines illuminated here. So finally then, I can do the final answer here. So I have delta lambda, that's my smallest difference in wavelength. It's just going to be the 620 times 10 to the minus 9 meters. Divide that by 2 times 12,000, which is 24,000. And there's no units on those, so that's why my answer will be in meters, which is good news. It's supposed to be. So let's see here, 620 times 10 to the minus 9. Divide that by 24,000. And what do we get? Oops, I need to make sure I put brackets or else I'm going to mess it all up. There we go. I end up with an answer of, oh, it's really small, isn't it? 2.58 times 10 to the minus 11 meters. This is actually my, this is a very, very small number, isn't it? I mean, this is tiny, tiny, tiny. That's good news. That's because a diffraction grating is pretty accurate. Not accurate, it's pretty good tool to use. Now let's just take a look at how many significant figures I can use. If I use 2 like this, so I can say 2.6, let's just say, because I'm using 2 here. So 2.6 times 10 to the minus 11 meters. This will be my smallest wavelength that I can actually image here. So there we go. So I hope you see that, although it seemed kind of crazy, we can completely do this, right? The trick was to not panic, first of all, when you see this equation, or when you see this kind of situation happening. Again, just try to break it down and decode it into what you really need. Again, this equation isn't actually so bad, is it? It's just r is lambda over delta lambda equals mn. You just have to know what each of the variables means, don't you? I really think of it, it's almost like, wearing a decoder ring. You sort of have to look at the question, sort of decode it. What do I have? What am I looking for? What equation will I use? And in these kinds of situations, they're actually pretty easy. They're actually not so bad at all. So that is Resolvance. Yahoo! I'm going to talk to you about Doppler effect. I love this little drawing here, this little sticker. If the sticker is blue, you're driving too fast. Why is that? Because if it's blue shifted, right, because I took this thing red, and if it looks like it's blue, that means it's blue shifted. That means you're driving so fast that you're actually approaching them. It's a lame joke, but there you go. So we're going to talk about Doppler effect, and there's 2 different versions. You can have it when you have a moving source or a moving observer. I'll just show you one of the examples, but you'll see the other one, it works just the same way. So you have to imagine this. You have a source of sound, and that one is moving. Okay, so just imagine that's happening here. So I'm a sound source, and I'm just moving along like this, so from left to right. What happens is, as I'm moving, I'm emitting a sound. Let's just say it goes like boom. It goes like out in a circle like this, like right from where you left it. And then, of course, you move a little bit and you send out another sound, so to speak, and then another sound. So that's what I'm actually trying to show here on this drawing. Can you see that? Just to show it. So let's just say I was a source and I was actually right here, for example. I would emit a sound here, and that sound, of course, would go out, wouldn't it? Like this thing would sort of radiate outwards. But the thing is, then I move along and I send out another one. But when I send out this one here, this other one here already got big and it moved. So this is the effect right here. You have to imagine it's almost like you've got circles and you're moving them. So that's why the circles get sort of squished on the front and sort of more space behind it. That's because this source is going to the right here. We're going to assume that this source is going this way right here. You can see that by the squishness of these waves here that have been sent out. It's a little bit hard to draw this because this is a dynamic situation that's actually happening and moving, whereas here I'm trying to just draw like a snapshot of what's going on. But basically what happens is as you emit these, these pulses of sound, for example, whatever these are, they're going, if you were not moving, they would just go out radially outwards. You'd see these nice, can you imagine, like let's say I set on another one, there'd be another one, and then there'd be another one. Like there'd be nice even spaces. The problem is they're not doing this. I'm not staying still. I'm moving. So you can see as I'm moving, I'm sort of squishing them as I send out another one and another one. So just, this is what's going on here. I just wanted to maybe try to show this just so it makes maybe a little bit more sense here. So what I'm going to do then is attempt, well, let's just see here. Can I grab these and delete them? We'll see if I can just delete a few of them later here. There we go. So with my moving source, and here's what's happening. I'm sending out this sound. Now remember though, if you look here, these, do you see these little differences right here? These are actually the difference in the wave fronts. So you could actually define this distance right here. You could say that's lambda. So is this. Now compare that lambda to this one over here. Look, this lambda here, I mean, I didn't draw it perfectly. These should be even spacing here. But do you notice this lambda over here is smaller than that one? So here's a little trick for you. When you have lambda is smaller, that means you have a larger f. That's because lambda, the wavelength, and the frequency work in opposite directions. If you forgot that, you can use the wave equation, v equals f lambda. You know, that's the speed of the wave, and this is the frequency and the wavelength. So if you want to do this, can you see if v here was going to be the same? If lambda gets smaller, then f has to get bigger. So this equation is sort of helpful in order to sort of figure out what happens here. So if lambda goes down, the frequency has to go up. They work in opposite directions in that sense. So what this then means, think about this. If you're observing this sound here, this is a sound coming towards you, well, the wavelength of the sound is smaller. Doesn't that mean then that the frequency is larger if it's coming towards you? So that means here, as it comes towards you, you're going to hear a higher frequency as it comes towards you. And of course, as it passes by you, can you imagine now this whole thing right here being sort of over here now? Can you imagine it being to the right? Do you notice that then you'd have larger wavelengths? So if you had larger wavelengths, that means you'd have smaller frequency. And the frequency really kind of tells you what we call the pitch of a sound. So, you know, if something has a higher frequency, it's like, you know, like you might have seen this with car racing. As a car passes by the camera, for example, you know, if you're stationary observer and there's a car coming past you, it kind of goes, why does it do that? Because as it's coming towards you, the frequency is higher. That's why it's like, I know I sound like an idiot when I do it, but that's fine. As it goes, and as it passes in front of you, of course, then it's going away from you. So larger wavelength, lower frequency. That's why the sound seems to go down in pitch. It goes, keep in mind, that's sort of how it works. I know I'm sounding like a moron when I do it, but there you go. So this right here is the Doppler effect equation. This is the main one right here that you need. And we're going to talk about this because you're going to have observed frequencies and emitted frequency. So this is why it's really important to then break down this equation here. So f prime is going to be the observed frequency. That's what you, the observer, actually detect. It's going to be equal to f, which is the emitted frequency. That's what it's actually putting out. You know, if it's like honking its horn, for example, or something. By the way, frequencies, those are measured in hertz, aren't they? Or in 1/seconds. Then you have v. This v and this v are the same v. That's the speed of sound, which is in meters per second. So if it's an air, it should be like, I don't know, 330-ish meters per second. And then us here, this is the speed of the source. That's how fast the source is actually moving. This is also in meters per second. So it tells you basically the faster your source moves, you know, the more this shift should happen. Now, when do you use the plus or the minus? There's some ways. I mean, you could actually try to calculate it. You could learn the different ways. But what I like to do is just think about very carefully. If this thing is coming towards you, you know the frequency should be higher. You know, like if it's coming towards you, frequency should be higher. So which value of us plus or minus would make the frequency observed be higher? You know, so which one would make that f prime to be larger? So would a smaller value on the bottom, see, if I did a smaller value on the bottom, that would make this value bigger. So that's how I sort of think about it. Otherwise, you can always just try to do both calculations, and whichever one gives you the larger frequency, you know, if it was coming towards you, then you do that. Because if it's going away from you, it'll be the opposite sign. I guess then the frequency should be lower. I just think about cars coming towards me, and that tells me if it should go up or down. So that's why I said coming towards you is higher pitch or frequency, going away is lower pitch or frequency. So let's look at this. We have another helpful equation. This I'm not going to say much about because it's on your data booklet, but it just tells you a change in frequency over the emitted frequency is equal to change in wavelength over wavelength, which is related to V over C. This is helpful for astronomy. for example. If we observe something's wavelength being different, then can you see that we can actually infer its speed as a fraction of c? So you see this one here? Do you see this? C, remember, the speed of light. So we can actually say then that, if we see the wavelengths of what we're seeing in a star, let's say we see some emission lines or some absorption lines or something that we're looking out into space, and we see something. And we see those lines, they're shifted a little bit, either blue or red. Right? This is the whole idea about red or blue shift. We say things are shifted because if they're shifted to larger wavelengths, that means they get more red. And red shifted means, things are going away from you. And blue shifted means they're coming towards you. And it turns out almost all the objects we look at in space, they're pretty much all red shifted. In other words, everything is going away from us. So this shift, this amount that's been shifted by wavelength, that's this delta lambda. So from there, you can sort of figure out your speed as a function of c, as a fraction of c, I mean. So here's an example. So here you're driving your car at a constant speed and you honk your horn, which has a frequency f0. Okay, so we're going to assume that we have some sort of frequency f0 here. Now at time t equals 1 second, what are you going to do here? You're going to pass a friend who's standing outside. So imagine then, so you're driving your car right here like this. Oh boy, that is a bad car. This is me in my car. I'm not an artist, you can tell. This is me driving towards my friend here. He's sad because he thinks I'm going to crash into him, maybe. Because clearly I'm not a very good driver if I'm not even in the car. I'm sort of outside it. I don't know what's going on here. So this is me honking my horn, right? So my horn sound is coming towards him. So what's happening then? Remember, draw a graph of f versus t for the variation of the sound wave. So what's going to happen is this. I'm going to be, well, let's assume we have some sort of constant value here. This is what this is what my actual sound is, which is f0, let's just say. And at this point, this is the important thing. I pass my friend. Remember what happens as I'm coming towards, like moving source, as I'm coming towards higher pitch or frequency. Remember, that's because the wavelength got squished. And remember, if wavelength goes down, frequency goes up. That's why I think of it as I just think of it, the wavelength gets squished in the front. So squished wavelengths means larger frequency. Therefore, if this is the center, this is like what I'm really honking at. That's the frequency if you were stopped. What will my friend hear? Well, before I pass him, so before t equals 1 second, it's going to be some higher frequency. And then as I pass it, I mean, it's not sudden. It's going to, it's going to be a transition like this, and then it's going to go sort of something lower like this. So I'm going to go from a higher frequency to a lower frequency than the emitted one. I hope that's easy. That's actually pretty straightforward, isn't it? I mean, you can do other calculations, but I mean, this gives you a good understanding of Doppler shift. So I hope that helps. There are lots of important equations when we talk about fields. I really like this image here. This is from, do you remember Felix Baumgartner? A few years ago with Red Bull, he jumped from extremely high up in a balloon. So anyway, so he has so much potential, I get it. So what I'm going to do is show you some of the equations that show up on your data booklet. And the reason I'm going to do this is because I really think that this particular topic, a lot of the times it's just a matter of decoding what they're asking for. In other words, I don't think that many of the questions are that difficult. It's just that you need to be able to look at the question and figure out what is it they're really asking me for. So that's why I've got this big giant mess right here, because this is the way it looks on your data booklet. Keep in mind the green ones aren't quite there. The green ones are off to the side, but I'm going to put them in here as well. So if you look at this, first of all, the left side is all gravitational and the right side is electric. So if you know how it works for gravitational, then you know how it works for electric. What I think is really interesting, to see how tantalizingly similar these different equations are to each other. For example, the gravitational force, look at this. It's a constant times a mass times another mass divided by the distance between them squared. Whereas the electric, it's a constant times, instead of a mass, it's a charge. So there's two charges times the distance, divided by, the distance between them squared. Do you notice they look really similar, don't they? And this is what I think leads a lot of people to think that maybe there is some sort of grand unified theory of the universe, because look at least the way the mathematics look. So it seems like, I mean, obviously since physics, or at least mathematics, seems to be the language of the universe, maybe there's something to it. We haven't quite figured out yet exactly how gravitation, for example, and electromagnetism are related. But doesn't it look kind of similar? So let's actually start by decoding things. Okay, first of all, I'm going to jump around a little bit. I'm going to start with some of the easier ones, just so we can sort of get going a little bit here. So let's label this right here. What is EP? I hope you know. I'm going to write grav everywhere for this, but this is the potential energy. That's what this is. This is potential energy. So are you okay with this? This is gravitational potential energy measured in joules. This is the electric potential energy. So electric potential energy. And again, this is measured in joules. So, and this is the gravitational. So the reason I'm doing this is just because this is one of the easier ones, isn't it? Most people see that E with little subscript P. Usually you know that that's electric or gravitational, but potential energy. So that's usually okay. So is this one right here, I hope. This FG, that's a grav. I hope you're okay with the grav short here. Gravitational force. And what's force measured in? Newtons. Well, then if that's a gravitational force, this must be the electric force, which is measured in, oddly enough, newtons. Of course, we've got the charges, which are measured in coulombs. Here we've got the masses. We've got the R's, which is the distance. Most people know those. So do you see we've already labeled some of them? Now comes the slightly sneakier one. So let's do this one right here. This one right here is the gravitational field strength. We saw these in another chapter, right? So this gravitational field strength. That means this must be the electric field strength. Now, what kind of units can we use for these? We have another equation for gravitational field strength. I mean, yes, we could say it's meters per second squared, for example, for gravitational field strength, but I think it's better to do the other equation that we have, which goes, so what is it, G equals F over M. So in that case right here, it would be in newtons per kilogram. That's the one from the SL topics. So that's maybe the better unit for it. Just like electric field strength, well, it'll be in newtons, but instead of kilograms, we have coulombs. So that's that. Finally, now comes the weird one, which is this V here. So I'm going to label these right here. This right here is called the electric potential. And I don't mean potential energy. This is going to be really important. You notice we had potential energy. Here we have electric potential. That's it. Just electric potential. Just like this here is called the gravitational potential. And again, we don't have any other things going on. It's just gravitational potential. So that might seem a little bit weird, okay? Because you're used to seeing like potential energies. Here we just call it potential. You might be more familiar with the electric one because we've been talking about a potential difference. But that's why this V here, you know, that's the V that's measured in this case here, volts. But you could also say another unit, and I'll show you why it is. I notice this is joules per coulomb. And this one right here will be in, let's see, this would be in joules per kilogram. How did I know this? It's not that I'm super clever. I just looked at this equation here for work. So I'm going to define that one as well. So this here is just the work done. Work done. And work is a form of energy. So it's measured in joules. So what I've done is I didn't quite know what units I should use here. This one has some weird units because of G. But look at this V right here. This gravitational potential. That's the same one that's right here. So because of that, in my head, I just put W divided by M. Okay, you see that? That gives me work, which is in joules, divided by the mass, which is in kilograms. Same thing over here. This electric potential is work divided by Q. So that's why it's joules per coulomb. Now, this may not seem super obvious to you, but actually, this is everything you need. This is all the equations you're going to be using in this chapter. So, well, especially for this section here. So you might have the force of attraction between two objects, or you might have the force of attraction or repulsion between two charges. We have the gravitational potential energy, like I said, EP. Do you notice we have another version of it right here too? Look, we have VG right here. And can you see it also looks the same? Look, it still goes. If I wanted VG by itself, couldn't I do the gravitational potential energy divided by the mass to get VG? And again, I get the same units of joules per kilogram. Same thing with the electric, right? The electric potential energy. If I wanted the electric potential, VE, by itself, I would just do EP divided by Q. And again, joules per coulomb. So this all is self-consistent at least. And then we've got the gravitational field strength. That's this G, which is the same as the acceleration due to gravity on Earth. And we have electric field strength, which is just this other quantity. And in this case here, it's the change in electric potential divided by the change in distance. So it's basically how potential changes with distance. And then we have these sort of more raw and pure equations here. Now what I'd like to do then is go maybe a little bit deeper in this one right here for gravitational potential. So for gravitational potential, remember that's this VG here, and this is just like this VE here, electric potential. I want to look at this equation again. So this W equals M delta V. This is on your data booklet. The reason I wanted to look at it is because the definition of it is in the equation. And I've seen quite often on exams, you're asked to literally just define what is gravitational potential. So can you see, you can actually say, well, gravitational potential is, can you see it's just work over mass? Like that would just be this equation. I'm just rearranging it. And there is your definition. Look, it's the work done per unit mass. And then we define it as this. We define it as, this is a little bit weird actually. What we do is we consider that off to infinity, so at a distance of infinity, we consider that to be where the energy is zero. So because of that, if you're going to bring an object from zero all the way to you, its energy actually goes down when you come closer to you, right? Its potential energy goes down. You know this because, if you lift something up, it's got a lot of gravitational potential energy. If it's down lower, it's lower. So in this case, you start off at zero already, and that means when you bring it closer, it's lower than zero. So in this sense, this is really weird, but that's why it's actually negative. And we can then use this equation here that, can you see this VG here is proportional to negative 1 over R? So that's what I'm going to write down here. I'm going to say that. So I'm going to say, maybe I'll do it like this. So I'll say VG is proportional to negative 1 over R. Do you remember what a 1 over X graph looks like? Normally a 1 over X graph goes like this. So negative 1 over X flips it across the X axis. That's why this right here goes like this. This is the VG graph. It looks kind of weird. And a lot of people really struggle with this because this is not that intuitive. My favorite way of seeing this is almost when you see it called a potential well. I kind of like calling it that because it almost implies like you're in a deep hole and you have to climb out of it. And in that sense, you can say you have to climb out of the potential well in order to get really far away. And we're actually going to define that as the escape speed, for example, is what speed do you have to go in order to climb out of the potential well. Of course, we have the same kind of definition we can do for electric potential. In this case, it doesn't have to be a negative. It'll all depend on the charges. But we, again, define it as the work done per unit charge to bring a small charge from infinity to some point. And that's kind of all we need there. And finally, just a very minor thing here, we got these equipotential lines. That's where the gravitational potential, remember that's VG, or the electric potential, VE, is the same. So these are places where, these will usually be sort of nice straight lines like this right here. These will be places where the gravitational potential is the same. It's almost like, I imagine like with water waves. If you saw water waves and from an airplane, for example, you're watching them, you'd see these sort of crests here, these places where, maybe the water has the same amplitude, or not actually amplitude, maybe they're all crests actually, like the top of the wave. Like a side view could be, where like this here, these would be like these places right here. From the top, you'd see these as these lines. Those would be places where instead of the crest, would be the same for the water analogy. This is the place where the gravitational potential would be the same, or the electric potential. So these are things called equipotential lines. Again, I like it because the word tells you everything. Right? Equi means equal, and potential means this VG or VE. So this is where the VG is equal or VE is equal. And that's all you need. That's all the theory you actually need to solve a whole bunch of different kinds of questions. Let's try it out. Let's do some examples with electric fields. So here we have two parallel charged plates, and they're separated by distance d. So maybe I can start by drawing that. Let's see here. So I've got two plates. I guess you don't really have to draw them, but I'll draw them. I'll attempt to. Here's one plate. Here's another plate. I'm trying to show some perspective here. Ooh. And I have a distance d between them. All right. We have a potential potential difference, sorry, of V across them. So this is a potential difference of V volts. This would be D in meters, I guess. Now we know that the electric field strength between them is E. So the question is, what would be the electric field strength between the plates if the distance between them is doubled? So basically we're looking at what happens if you make 2D. I think it really helps with something like this is to write this down as a ratio. So what I'm going to do is first start off with, I need an equation for the electric field strength between two plates here. And you can go searching for your equations, but if you see on the right side of your data booklet, you can see that there's an equation that goes E equals minus, let's see here, delta VE over delta R. This is the equation I'm going to need. So we can say, okay, well, this is what happens here. Look, we have E equals basically the the difference in potential over the distance here. So in this case right here, I could just define it as V over D. You okay with that? See what I've done here? And the minus isn't so important. It all depends on if it's a positive or negative charge. So we could leave the minuses, but when we do a ratio, they're going to cancel out anyway. So this is what I have in general. What I always like to do is write a second one, like this is my new one. What have I done here? Here I've changed things. I haven't changed my potential difference. That's the same. But the distance is doubled, so that means it's over 2D. And again, a nice generic way to always solve these things is to just write these two things one on top of each other. So put E2 over E. Well, that's going to be, let's see, the equation for E2 is V over 2D. The equation for E is just V over D. I know I'm doing it in painful detail, but that's just because some people like to see all the detailed steps. That way I don't skip any. But if you're going to divide a fraction by a fraction, then you have to multiply by the reciprocal. So in this case here, it'll be D over V. And good news, the V's will cancel out, the D's will cancel out. You'll end up with E2 equals, let's see, I have a 1 over 2 here. And I have my E here that I need to then bring up to the side. So it'll become E over 2. And this will be my answer. You see how easy that was? Easy, huh? That's because what we were able to do here is just consider the effects then of changing the distance. If you're a little bit faster at doing this, you don't need to write down all these steps. A lot of people, once you know that you're changing things, you know that the things you're not changing will cancel out. So, when you get a little bit better at it, you don't have to do all these steps. But that's okay. I just wanted to show you every step just so I can do it. So you can say, so doubling the distance between the plates makes the electric field be half. That should actually make sense because it's directly proportional to V and it's inversely proportional to D. So if I made D 2 times, then this obviously is half. So you could have seen it almost immediately just by looking at it. I just want to show you how to calculate it. Now comes actually a pretty easy one. What's the electric potential at a distance of 2.2 meters away from a point charge of this many nanocoulombs? You just got to watch out. So here we're looking for electric potential. We need the equation then for electric potential. So I'm going to go look for one. And I'm looking on my data booklet for one for electric potential. I have this one, KQ over R. It's not squared, it's just KQ over R. This is the electric potential. Remember, that's measured in volts. Well, actually, this is really easy. Look, this is one of those, it actually came up on an exam before. I just thought this was really nice. It's a piece of an exam, obviously, but I thought this is really pretty straightforward. Look, you just put in K. You can look it up. What is K? It's 8.99 times 10 to the 9. So this is what K is. That's just K. Q then is 0.39. But then I have to do times 10 to the, and watch out, nano means minus 9. Again, if you're not sure, you can always look it up. Actually, I'll just ignore the units. They'll all work out here. Divide that by R, which is 2.2. 2.2. So let me actually just try to do this on my calculator here. So I'm going to do 0.39 times 10 to the minus 9. Multiply that by 8.99 times 10 to the 9. Divide that by 2.2, and I get 1.59 something. And I'm only allowed 2 significant figures, so I'll make it 1.6. And this will be, let's see, what's the units of electric potential? It's volts. You see, actually, this stuff doesn't have to be so bad. Like I said, a lot of times the key is just decoding what it is they're asking for. Find yourself an equation, even if they look weird. It's usually how you solve them. Finally comes a nice easy one here. Draw the equipotential lines between 2 parallel plates. So remember, equipotential lines are places where V, in this case here, VE is the same. Okay, so they're places that have the same VE. If you think about it, electric field lines, don't they go this way? I have the electric field lines, they would go that way. You know, because electric field is the direction that a positive point charge would go. And the way I like to remember is equipotential lines are always perpendicular to field lines. So that's why they'll go like this. Let's just see here. Oh, by the way, what will happen then like this right here? At the edges, they'll go like this. You know, if this right here is the, this is, by the way, these are the electric field lines. That's not potential. But I'm just trying to show you that actually they're perpendicular to each other. So this here is a bunch of pluses here, and this is a bunch of minuses. The electric field lines would do this. And most people are okay with this. Just imagine a little positive particle, throw it in there, let it go, and you'd see what would happen. So in this case then, think about this. The equipotential lines are perpendicular to this. So that perpendicular means 90 degrees, so watch carefully. That means I would make it like this right here, but even let's even go a little bit further and see where it curves. See how it curves like that? It'll actually curve a little bit this way. Like that. That's how I could draw it. So if I'm really, really careful, I could draw a line straight down. Whoops. I could draw a line maybe a little bit curved. And I could draw another one that's a little bit curved. Whoops, I meant to not make it curve so much. I just kind of messed it up. I didn't make it look like it went down very much. This should be straight down, and after that it should curve just at the edge here. Just like that. So this should be parallel within the plates. They should just curve a little bit at the edges. That's it. These are places where the electric potential is the same. So I don't know what the value is. Maybe it's like 10. Then it'll be 10, 10, and 10. So these would be places where it's the same. Do you see how, sorry, this would be 10. Sorry, this might be 5. This might be 8 or something. I mean, they'll be different values, but these lines mean that everywhere on this line is where it's the same. So for example, let's just say I decided it was 10. That means here it's 10, here it's 10, here it's 10, here it's 10, here it's 10. Here might be a different value. It might not be 10. Maybe it's, I don't know, 2. Then here everywhere is 2, 2, 2, 2, 2, 2, 2, and so on. So I mean, the numbers, well, you could always work out how they go because of the pluses and minuses. But I'm just saying these are places where it's all going to be the same. I hope that helps just to put it together, and you can see that they're actually not so bad at all, the kind of questions you get on the exams. They're not bad at all. I love this picture of Newton. You don't understand the gravity of the situation. So we're going to talk about orbital mechanics. It's something that sounds really complicated, but it's actually pretty straightforward when you really think about it. Well, hopefully at least that'll be the case. So let's talk about an orbit. Remember what it means to be an orbit, right? It means that you have an object that's gravitationally attracted to this other object. They're both attracted to each other, so they both orbit a common central mass. It's not that the heavy one just stays still, right? They both move a little bit, and they both wobble. But we're going to consider just the one that's orbiting around. So that's what we call it a satellite. A satellite is anything that goes around. So for example, the moon is a satellite of the Earth. So in an orbit, a satellite of mass m, that's a little mass right here, it's going around a planet of mass capital M and has an orbital radius of r. Now, keep in mind, we're going to assume that the orbits are circular. Kepler, a long, long time ago in the 1600s, he figured out they're not circular, actually, they're elliptical. But we don't need to know that for the IB, where you can sort of skip that. But in real life, just so you know, orbits are actually not circular, they're elliptical. And then we talk about ellipticity, sort of how sort of egg-shaped it is kind of thing, or how elliptical it is. So you can have a special case with an ellipse is to make it a circle. So we're going to consider nice, simple circles. The good news is it's very close to what the real math needs to be for ellipses. So let's talk about the kinetic energy first, in general, for anything that's in orbit. Well, the kinetic energy in orbit, I hope you see, it's really simple. It's just the equation you know. EK equals half mv squared. Nothing brain-busting there. Now, the potential energy in orbit may not be so easy. You might think, oh, it's mgh, right? That's only on Earth at the surface of the Earth. So that's why you have to look up in your data booklet, where's the equation for potential energy? If you look past another video, I showed you it, but the potential energy equation goes like this. It's minus GMM over R. You find that one in your data book. It's on the right side under fields. So if you look at this, there it is. Okay, fine. Let's look at maybe a graph of each of these then. Let's maybe do those. So we'll do a graph of EK. Actually, just wait a second. What I'm going to try to do, let's see if I can do these in different colors. If I don't mess it all up. No, I think it's going to mess it up. Oh well. So what I'll do is I'll draw the kinetic energy with respect to r. Now this is going to be the actual surface of the planet. Okay, so let's say you start off here. Let's do it realistic, right? You can't have negative radius around the planet. So let's say you start off at the surface of the planet, and you try to escape that planet. Can you see you're already at this surface right here? You're already there, so you're already at this planet where it starts. And then you go and take off. So you're in an airplane or in a spaceship or something, in a rocket, and you have an initial velocity. In this case, it'll be a very large velocity probably if you want to leave at least, or you eventually have to get to a large velocity. But in order to orbit around something, the way that the speeds work, it's kind of interesting. It goes like this. Watch, I'll do a drawing of it here. Kinetic energy at least will go something like this. So kinetic energy will actually drop down like this right here. This will be EK. So what does this mean? It means that depending on your orbital radius that you want to have around this planet, as you go further and further out, you need less and less kinetic energy in order to do it. So you won't need as much kinetic energy. In other words, you'll be going slower. Can you see at r equals infinity? Imagine you go r like all the way to the end of the universe. Can you see that you technically have then no kinetic energy? If that makes any sense. But you start off with some kinetic energy because you're clearly, you have to be moving in order to do something. So I hope that makes sense. This graph goes like this. It's not super intuitive because here we don't have an equation with r, we have an equation with v. But hopefully you see this is the case. Potential energy, however, that one should be straightforward enough. We have r in it. And remember, it goes, potential energy is 1 over r, and it's negative. And a graph of 1 over r would go like this, so negative would flip. It's not quite symmetric, okay? This one here is actually more negative. I don't know if that makes any sense. This one here, this is EP here. Because it goes just like the gravitational potential. The potential energy does what the gravitational potential does. So keep in mind then, the total energy, how would I find that? I hope you know ET is just EK plus EP. So in this case right here, let's add them up. So I have half mv squared. Plus, but I'm adding a negative number, so negative GMM over r, just not r squared, but just r. This is the equation for total energy. What does that mean to do here if we wanted to do the graph of it? Because you could be asked this on an exam as well. It's not going to be 0. Like I said, the potential is more negative than the kinetic is. So in other words, they don't just cancel out. Actually, the total energy goes somewhere in the middle, goes somewhere like that. So this is ET. And this suffices, this is enough for exams. So if you're asked to do a plot of these different things, this is how each of them goes. It's not super intuitive, right? You'd think that your total energy should be positive, but like I said, the negative potential energy is caused by the negative gravitational potential, which we defined as, 0 at infinity, which means it has to get less as you get closer. So that's a little interesting little thing here. Let's go to the next one. Escape velocity. This one I love. Because if you want to leave a system's gravitational field, I mean completely. Whoops, I didn't mean to say need. I realized I had a spelling mistake. This is just like, all right, so at least I may as well fix it right here. So you need to go to a distance of infinity. So if you want to actually completely leave the gravitational field, you got to get to a distance of, the end of the universe or whatever. So at infinity, we define the total energy to be 0. This is the key part right here, okay? That's the part you need. Whoops. I'll do undo for that. What I meant to do was start drawing in green here. So what I would say then is ET equals 0. So here's how we can actually find the escape velocity, okay? Well, it's the minimum speed you need to go in order to reach this distance of infinity. And this is the key stipulation we say. We say the total energy equals 0. Well, remember again, the total energy is just the kinetic plus the potential. I'm just figuring it out again just to show you. If I need to know the kinetic, well, I know it's half mv squared. If I need to know the potential energy, I can look it up in my data booklet, and it's negative GMM over r. That's just what EP is, and it's negative. Well, then if I set ET equals 0, you see that? I'm just going to show you all the steps just to show you the derivation. It's not that hard, though. But you see now I can move the GMM over r maybe to the other side. So now I have GMM over r. That equals 1/2 mv squared. See, I've just moved that whole term over. Luckily, the m's cancel out. That's kind of nice. And I want to get v squared by itself. So I'm going to put the 2 on top. So I'm going to have 2gm over r. And that's going to equal v squared. So if I want to get v by itself, it's technically plus or minus, but we'll just consider the positive version. This is the equation for escape velocity, or escape speed. So if you want this one right here, I would maybe even label it with a little escape, like ESC. It tells you how fast do you have to go in order to completely leave a gravitational body's influence. For example, on Earth, if you put in the mass of the Earth and the radius of the Earth, you get something along the order of 11 kilometers per second. So for example, on Earth, that's what it is. So that means if you want to completely leave the Earth, you got to go something like 11 kilometers per second, which is crazy fast, right? In 1 second, you got to go that fast. Well, yeah, that's to completely leave. I don't mean that to get into orbit around the Earth. There you can have lots of smaller, slower orbits. This is the speed you need to leave Earth, to go somewhere else. For example, oh, I don't know, Mars or wherever else you want to go. Okay, that's the escape velocity. You need this to get to infinity, basically. You could have less, like I said, to be in orbit, but this is roughly what you need to escape the Earth. Pretty cool. Finally, we got the orbital speed. We've kind of done this before in the SL portion, but let's do it again here. So we have a satellite of mass m, and it's orbiting a central mass, capital M again. And we're going to consider the orbital speed. To do this, what we have to do is just consider the forces. Remember that you've got a gravitational force between the small mass and a large mass. So that's given by gmm over r squared. You can look that one up, right? That's at the bottom of that topic. And then, because it's going in a circle, you have a centripetal force. And that centripetal force is mv squared over r. You can find that in another chapter from the SL core. Then if we consider this then, well, the centripetal force is caused by the gravitation, so that's where we set Fg equal to Fc. Therefore, we get gmm over r squared equals mv squared over r. The little m's cancel out. And this r right here, if I bring it up to the top, that r will cancel out that one. So there we go. And we're left with, let's see here, v squared equals gm over r. Now what I think is really interesting, do you notice, by the way, it was different than this right here? Look, there was a 2 here, so it's not the same here. The escape velocity came from kinetic plus potential being 0. Okay, it's very, very different. Do you notice there's a 2 here? I know it looks the same, but it's not quite the same. So therefore, the orbital speed then would just be, just take the square root of that, so it'd be gm over r. This would be the orbital speed. And you're given this on your data booklet as well, so you don't have to memorize this. But I think it's a good idea to know how to get to it, right? This is your orbital speed. So this tells you how fast you have to go in order to be at an orbit of r from the center of the mass here. So you got to be very, very careful. If they ask you, what is it from the surface? You have to subtract 1 r from whatever your radius is that you're looking at. So you just got to be a little bit careful there. This is technically from the center of the object. So again, if you want to find out your orbital speed, depends on what you're doing here, but if you wanted to actually do this, what you can do is say, all right, here's the orbital speed from any given radius. So you can maybe, do it over here, maybe to some point right here. You just calculate, all right, well, that's going to be the r here that you're going to put in, is the r from the center of the object. That's the value you're going to put into this equation. Put in the mass of that body, put in capital G, which you can look up, 6.67 times 10 to the negative 11, and away you go. You got your orbital speed. I don't know about you, but I feel like doing some examples of gravitational fields. And since I'm the one controlling the video, you're stuck with me. So what we're going to do here is, actually maybe we should first look at this little cartoon here. So I put in, isn't this Wile E. Coyote from cartoons? I used to watch these as a kid. I like the first law of cartoons, right? That gravity doesn't work until you look down. You ever seen that? So he sort of walks out and then he sort of stops. He looks and looks down. Maybe holds up a sign like help, and then he falls. Obviously that's not how it works. Haha. So let's actually deal with something that's a real kind of question you could be asked on an exam. A planet has a gravitational field that is uniform, and I'll explain what that means in a second. Now we have the gravitational potential difference between the surface of the planet and a point 50 meters above is 20 joules per kilogram. That sounds a little bit crazy already, right? You're already probably starting to worry and hopefully not feeling like holding up a little sign that says, help. So we'll draw that actually. So this is maybe how you feel, right? Maybe you feel like holding up a little sign that says help. So, I mean, these kind of questions, I think, really cause people problems, right? But let's see if we can actually figure this out. Now, we want to know the work done. This is what we're looking for in bringing a mass from a surface to another point, and you might be thinking of throwing up already. But let's just think about, remember, you have to sort of wear almost like a decoder ring and sort of look at the question, like, all right, what do I have to do to solve this? What am I looking for? What kind of equations do I have? Remember I said you don't have to be super awesome at physics to do these kind of questions. Just be good at decoding the question. In this case, we want work done, and we're given things like gravitational field. So let's quickly, just to show you how to solve this sort of as a non-expert in this stuff, what's a gravitational potential difference, first of all? Do you know what letter that is? That is Vg. That's what we're told here. So we're told some values of Vg. And we have a distance and we have a point, so we have some sort of delta R's going on. Like we have some Vg's and some R's. And we want to know the work done. This is what we're looking for. So I think it helps to look at, well, what are you actually looking for? You want the work done, and it has to be somehow related to maybe the gravitational potential. So let's see if we can find that. So can you look in your data booklet for an equation that has W in it that has Vg? I hope you can find it. It actually goes, well, let's look it up here. Where is it? I'll just write it down here. So, and I think it's a good idea actually to even write down what you know, right? It's a good idea to write down what you're looking at. So in this case here, I'm going to write down the equation. It goes W equals M delta Vg. This is the equation we're given. This is the equation that we're going to use. So if we use this, do you notice the work done then? I need to know the mass. Got it. I got that. I need to know delta Vg. Uh-oh, I don't know that. So do you see how this is now the goal is to find out what's this? See, I need that in order to solve W. So let's maybe look at this, what this Vg means. Now they tell me that the gravitational field is uniform. And actually, maybe before I do anything else, maybe it's a good idea to draw it. So I'm going to draw myself like a planet here, and I'm going to draw myself a point that's 50 meters above, so maybe I'll consider, I don't know, maybe this is going to be 50 meters above here. So if I do that distance right there, let's assume that's 50 meters. Then I know that the gravitational potential difference is 20, so I know that right here it's 20 joules per kilogram. I know that that's Vg here. That's the Vg, from going from the surface to here. That's the delta Vg from zero, well, from the surface to here. Okay, now we're told basically we want to take an object and not do this. We want to bring it to a height of, where is it, 20 meters above, so a little bit less than half, so maybe something like this. I'm looking for something that's 20 meters instead. I'm looking for that. Here's the problem, and it may not be clear. How do I deal with this? I think the key to doing this is reading this first part of the question. Gravitational field is uniform. Do you know an equation for gravitational field strength? That's this equation G. And if you look it up in your data booklet, what is it? It's delta Vg over R. This is how it goes. Delta Vg over delta R. This is how it goes. And if it's uniform, what that means is it's the same at both cases. In other words, it's the same, this delta Vg that we're just given with this change in R. We know that that ratio will be the same as the other one. I think that was the not obvious part. I thought that was the key part to solving this, because otherwise you're kind of stuck. So do you notice then, if G is constant, in this case here we're told that G is constant because it's uniform. This is what implies that. Okay, we know that that's constant. Because it's constant, the two Vg over R's can be the same. That means that now I can solve this. Watch carefully. If I do the Vg right here, I can do 20. And of course, the negatives are going to cancel out, so we don't have to worry about the negative. So let's do the Vg that we know. We know that 20 over this delta R, which is 50, that's going to be the same as the delta Vg, which I'm looking for. I don't know what that is. Divided by the delta R, which I know is 20. Can you see then, you can then find Vg. Vg is just going to be 20 times 20, which is 400. Divide that by 50, I end up with, let's see, 50 into 400. That's going to be, what, 2 in 100, so 2 times 4, that's going to be 8. So Vg is going to be 8, keep in mind, joules per kilogram. I'm going to need this. That's my, technically it's my delta Vg. Why did I need that? Because now I can use this equation here for work. I knew that the work was equal to m, I'll do a different color maybe. So now I find I know that work is equal to the mass times delta Vg, And I know my delta Vg is 8. See that? So I said my work is equal to 3.5 times 8. I can do that on a calculator. Let's see here. I can get 3.5 times 8. What's that? That is 28 joules. I have two significant figures, so I guess that's enough. There we go. 28 joules. That's how we can solve this question. Let's do another one. So I have one last. I think I just had two. Yeah, I have two questions for you. So these are all exam questions, right? So this is why it's a good idea to know how these work here. The escape speed on a planet with mass m and radius r is v. Now we want to know what's the escape speed if it has 2m and radius r over 2. Notice how often they like these sort of ratio things, right? This is a especially important equation or a question. So if we want the escape speed, maybe it helps to actually look up the equation, right? The escape speed is 2gm over r. You can look that up. That's in your data booklet. That's there for v escape. So what I'm going to do is, I'm going to call that just v. So in this case here, I'm just going to call it 2gm over r. That's just going to be v. Now what I always like to do for these ones is set up a new equation, call it v2 maybe, like a new one. That's my new situation here. And here I have square root of 2, and I have g still. But in this case, instead of m, I put in 2m. And instead of r, I put in r over 2. This is what I need to do here. Now, I think it's a good idea maybe to do v2 over v. And actually, I don't like these square roots. Those are making me a little bit nervous. So actually, what I'm going to do, I'm going to square both equations. This way, it's going to be a little bit easier to look at. So v2 squared is going to be, let's see, 2 times 2 is 4gm. All that's going to be, by the way, let's just figure out this one just to make it simpler. This is 4gm. And see this 2 right here? This 2 actually flips and comes on the top here. It's the 2 over r. Remember, because when you divide by a fraction, you have to multiply by the reciprocal. I'm just trying to fix this up a little bit. Because, this here is no longer a 4. This then will be an 8. Does that make any sense? Because 2 times 4 is 8. So this is going to be here 8gm over r. Divide that by 2gm over r, because that's the one that we have here. So if I do this, the gm over r's, they all cancel out, and I end up with v2 squared over v squared equals just 8 over 2, which is 4. Now remember, I don't want v2 squared, I want v2 by itself. So now I'm going to take the square root of both sides again. So just to make sure it's a little bit easier, take the square root of both sides, I get 2, don't I? So finally, I can state that, watch this here. So my new velocity, my new escape velocity is going to be just 2 times v. See that? Because my v can come over here. So see how we were able to actually solve this? It looked really complicated. But the trick was, write yourself down an equation for what you're looking for. And if things change like this, write yourself an equation for the new one. Divide the two equations and see what cancels out. In this case, we had to do some weird stuff with the square roots and the squares, but that's it. This is how you can solve this stuff with orbital mechanics. Yeah! Flux and Faraday's law. I know a lot of people, when you see this, you might be thinking like this t-shirt, what the flux? I like how they put, do you know what that movie is from? Actually, that's from a movie that I loved as a kid. It's called Back to the Future. So good. Perfect movie for me as a kiddo, that's for sure. But anyway, they had this thing. So it stars Michael J. Fox. It's about a time-traveling car, basically. And the thing that made it work, they made it sound really fancy. They call it the flux capacitor. So that sounds very sciencey, right? And in this chapter, actually, we're going to talk about flux and capacitance. So it's going to be kind of related, but not at all. We don't go back in time. But yeah, what the flux indeed. So let's talk about flux, what it is. It's a little bit abstract because we have an equation for it, and it goes like this. This is in your data booklet, so you don't have to memorize it. It goes like this. It's this phi here equals BA, and it goes cos theta. And this right here is the equation. That's it. That's all you need. There you go. So what does this really mean? First of all, this phi here, that's the flux. So that is what this is right here. That's this. We call this the flux. What is it really? It's related to the magnetic field strength. Now, remember what magnetic field strength is measured in? It's measured in Teslas. The area, now this is going to be some sort of surface here. It's going to be some sort of surface here that's being hit. And maybe actually I'll draw it like this. So what I'd like to do is show you that you have a surface. In this case, it's this nice, easy. I'm trying to draw a square, but that's in sort of in perspective in 3D here. So I'm attempting to draw like, I don't know, like, you know, a piece of paper or something, right? So you have a piece of paper, and so you have some lines that are sort of crossing it. And if those lines are sort of crossing this piece of paper, then we're going to call this flux. It's going to be related to the surface that these lines are hitting. So the flux themselves, those are basically these lines. Okay, so these are going to be these. The flux is this weird quantity, but it's related to these lines that are hitting this, these magnetic field lines. So in this case right here, if I've got magnetic field lines going, oh, I don't know, like maybe they're sort of crossing it like this, maybe like that. What this really means is that, you know, I've got some magnetic field lines that are sort of, well, actually maybe I shouldn't draw it like that. That's going to look confusing. Maybe I'll draw it from only half. So I'll do it from the halfway mark like this, maybe like that. So can you imagine, this is a magnetic field line that sort of hit it from behind. I just wanted to make sure you sort of got the idea of the perspective here. Let me try to imagine this thing here going across. I'm probably drawing it poorly, but something like that. Can you see it sort of behind this thing? Now it's coming out. And we consider this right here, this will be a magnetic field line. Okay, this will be B. This will be a magnetic field line. So in this case right here, maybe it's going that way. And what we're going to do is we're going to define this area of this surface. So that's why this area is going to be like a regular surface area. It's going to be, you know, meters times meters or whatever. It'll be meters squared. And theta is going to be the angle between B and A. Now, most people just think, oh, it's the angle between the surface and those magnetic field lines. But nope, I could not stress this enough. I've seen a bunch of times where they ask you for this. Okay, this is really important. Okay, make sure you know this, make sure you know this. Have I made this obvious enough? So it's the normal to A. So that means that's this angle right here, theta. Because what I've seen them do on exam questions to be sneaky, because you think they can't really ask you much here, except for what's the flux, see, what the flux, given B, A, and a theta. So the way they can be a little bit sneaky is they'll give you the angle, but based on not the surface. Let's just say it was like, let's say it's flat like this here. This is the surface, and we're seeing it from the side this time. What if they give you the angle like from here? They give you, this is the theta right here. That's the theta, you know, for this B line. Like this, you say, I use BA cos theta, right? Nope. You're supposed to define the angle from the normal. It's this one, not that one, not that garbage. Okay, so even if they give this to you, you can change it by then making it a sine. So if they're being really, really sneaky, then make it BA sine theta, then it's like, nice try, IB. I know how to solve this. Okay, so remember, it's from the normal. All right. That's about all we need. We just need to sort of define this. Because now comes one of my favorite definitions. It sounds really complicated, but it's from Faraday's law. Named after Michael Faraday, who did a lot of work on fields for sure. So this is one of my favorite sentences. And I gotta say, this is true. My own students in class, if I ever saw them like in the hallway, I would often just ask them, quick, what's Faraday's law? Because I think it's one of the nerdiest sentences, isn't it? And I love nerdy sentences, right? I'm a nerd. So here we go. And I don't mean nerd in a pejorative. I mean it in a form of endearment. So the induced EMF is proportional to the rate of change of magnetic flux linkage. Isn't that awesome? That just sounds so nerdy, isn't it? You know, someone says, like, instead of talk dirty to me, talk nerdy to me. Here you go. The induced EMF is proportional to the rate of change of magnetic flux linkage. You might be thinking again, what the flux? How do I do this? This definition, which you could easily be asked on an exam, is related literally to the equation. So watch carefully. You get this equation on your data book, okay? It goes E. This, by the way, is the induced EMF. This is going to be a voltage, as people like to call it. Okay, so this epsilon here, that's measured in volts. EMF is not a force in newtons. EMF is in volts. So the EMF equals, it's actually this. Wait, let's just see here. What does it mean to be proportional to? It means equal to some constant times. And a rate of change, if you think about that carefully, that's how something changes with time. So that's why it's going to have this d phi dt. And we're going to put an n here. And this is going to be the equation. I'm going to explain it in detail. You're going to see this equation will make perfect sense in just a second. First of all, this d phi dt here, this delta phi delta t, this is your rate of change of magnetic flux linkage. That's what this actually is here. This is how your flux linkage is changing. And then you have, of course, when I said it's proportional to, see, that just means EMF is equal to some number times d phi dt here. That's what proportional means. The negative, it turns out, that's to talk about Lenz's law, which we'll do in another video. It just tells you that the EMF is going to oppose the motion, so that's why it has opposite. So basically, this equation tells you everything. This equation tells you Faraday's law, because it's EMF is proportional to this d phi dt, and it tells you Lenz's law because it's the negative here, and just the number of turns in a coil. So what does this mean? First of all, the important thing is this: moving magnetic field lines, those induce a potential difference. That's the quote-unquote voltage. And this may not be clear at all, so that's what I'm going to try to explain is this. Imagine I have a magnet. Let's just say, I don't know, my calculator is my magnet. It's got a north and a south. Around that magnet, there are magnetic field lines going around it. So if you imagine then you've got these magnetic field lines that you can draw, and they're hitting a surface like, oh, I don't know, my little drawing tablet like I'm using here. Like this little thing right here that I used to draw. Whoops, I don't think you can see it very well. Like this little thing, for example, this is what I'm using to draw with. So imagine then you've got these magnetic field lines that are hitting this surface. Remember, that's how we defined flux? Flux lines was these places where these magnetic field lines are crossing your surface. That's your flux linkage. So if those field lines are crossing this object but not moving, you don't have an induced EMF. Nothing exciting happens. But if the field lines are moving, do you see it? That's where you have this d phi dt. That's where you have the rate of change of magnetic flux linkage. What that means is those field lines that are around this thing, when they're moving or changing, that's when you have an induced EMF. So only when they're changing, they got to be moving. So for example here, what I've drawn here, I've got a magnet, so north and a south. I've got a piece of metal, maybe it's like a piece of iron, and it's just got some wire wrapped around it. We call that a solenoid, or some people call this an electromagnet. But there's no current in here. This is just attached to like a light bulb. And this is the case, for example, with my bike. So in Denmark, everybody rides bikes, it seems. This is actually what I have on my bike, right? So what happens is this. I've got this here going on. So let's just draw the field lines around this thing. So if I want to draw the field lines around this, let's see. Field line, magnetic field is the direction a compass would point on north. And the north doesn't like north, so it goes away. So imagine I'm drawing this thing going like this. And another one going like this. I can draw little arrows. And I can even draw one more just to make it sort of, whoa, I don't know what happened there. Actually, maybe I'll just leave it like this. So watch this carefully then. If this thing right here, watch, if it's, whoops, come on, man. There we go. So can you imagine then this thing right now, as it's close like this, can you see the field lines are crossing this object? So there's flux linkage. Do you see that? There's magnetic field lines that are crossing this. Nothing exciting will happen now, but watch on the screen. Watch. If I go like this, like, I'm moving around like this. If I'm going, I'm moving around. It looks very dirty, maybe. It looks like it's doing something to it. But let's just say, so if it's moving around, no matter what it's doing, as long as it's moving, you will have an induced EMF because there's a rate of change of magnetic flux linkage. That's the key. So that is the important part here. Now we also have an equation here for the induced, for a moving wire in a magnetic field. We have an equation for that. It goes like this. Let's see here. EMF is just equal to BVL, where this is just L here like this. So this right here is the equation you need for this. It's the induced EMF. Whoops. So the induced EMF, what's that measured in? That's measured in volts. Magnetic field strength is measured in Teslas. Speed of the wire, that would be meters per second. This would be like a wire that's moving around in a magnetic field. And this would be the length of the wire in meters. And just to show you how you could quantify this, we have a plane and it's flying with a certain speed. So now we know V, right? We know V is 200. Has a wingspan of 30 meters. That'll be your length. And the Earth's magnetic field strength we'll say is, so B we'll say is 10 to the negative 5 Teslas. That's actually what it is most of the places on Earth. What's the maximum potential difference it can generate across its wings? Again, you just have to use this equation. Just V, V, L. It's that easy. So this is your induced EMF. So you just put in your B, which is 10 times 10 to the negative 5. We have times V, which is 200. And we have times 30. If you look at this right here, 2 times 30, that's 6 with, let's see, that's 6 with 3 zeros. I do that times 10 to the minus 5. So that ends up giving me an answer of, well, let's see, 600 times 10 to the minus 5. That's like 6 times 10 to the minus 2, isn't it? So, yeah, I mean, we can figure this out. All right, so this right here will be your answer right here. I mean, I think you can just leave it like this, can you? That's good enough. Yeah, Or you can say, well, 600, so this is here is 10 to 6. You can say 6 times 10 to the minus 2, which you could say 0.06. I guess that's a better way to write it. Volts. So this here is the maximum potential difference you could generate across the wings. So again, it's a nice simple equation, right? It just says induced EMF is B times V times L. This really does happen, right? So this you can really generate, a voltage across your wings, basically, if you're flying around, because there's a magnetic field. So as long as you're flying around in a magnetic field, this equation right here holds true. And again, just to reiterate, Faraday's law is awesome. It just tells you if you have a moving magnetic field, it's going to induce a EMF, which is a voltage. Now it's time to put Faraday's law together with Lenz's law. And that's another awesome thing here. So this is this one right here. It says that the induced EMF will act in such a way as to oppose the motion. What does that mean? This seems to be really weird, right? I love this. It's like, I'm not saying it's aliens, but it's aliens. It's like, no, there's not aliens going on, but it is a little bit weird seeming. So the induced EMF, remember from this equation that it's this is Faraday's law, right? That's this one here, that the induced EMF will be proportional to the rate of change of magnetic flux linkage. Again, what that means, moving magnetic field lines, those are going to create this. N is just a number of coils, so it just makes it bigger if you have more turns. It's this negative, that's the important part right here. This negative, that's the part that opposes it. So what does that mean? It means that depending on the situation you are looking at, you need to think about what's going to happen. So that's why I've got two examples here. So first one, in which way will the current flow in the wire at point 1? So here, do you notice we don't have a battery or anything? This is just a passive sort of circuit. It's just a coil of wire around a piece of metal. And now we have a north and a south. This is a magnet coming towards it. In this case, in that way, in sort of that direction. So what's really going on here? Well, it's going to oppose the motion. And what I mean by that then is this. Because it wants to oppose the motion, it doesn't want a north coming towards it. So because of that, it's going to temporarily, only while this north is coming towards it, it's going to temporarily make a north here and a south here. It's going to become magnetized, but only temporarily and only while it's going towards it. So then you can use your hand rules to figure out which one we should do. Now keep in mind this is a solenoid, so you should probably use hand rule number 2. Look back at other videos that I've made about the hand rules, right? This was from chapter 7, I think it was. No, 5, topic 5. So at the end of topic 5, I've got lots of videos on the hand rules. You'll need the solenoid rule here. So here you're going to have to use your, remember it goes like this, right? Like that. So that means your fingers are the current and your thumb is a direction of magnetic field. So it's the direction that a north would point. In this case right here then, you have to use your trusty right hand. In this case right here, you can look, I'm going to make my right hand, I'm going to make my thumb point to the right. Why is that? Because if I put a north right here at the end of my thumb, wouldn't that make the magnetic field lines go away from that? Because that's the direction a north on a compass would point. So in this case right here, my thumb, that's going to be north. That means, so that means to your piece of paper, do that. Okay, so put your hand like this right here, to a piece of paper, whatever you're writing on, or to the screen. Your thumb is that way, and then look carefully then what your fingers are doing. Your fingers curl in the direction of current. Can you see in this case my fingers are curling sort of out of the page, so to speak, and then this way? They're going like this. So look carefully then how to apply that to the screen here. So if you do that, does it make sense then that they're going, watch carefully, they're going like this, and the current's going to go in that direction. Can you see that? It's going to go out from behind this thing and in front of you, then behind, and then in front of you. So if that makes any sense, that means it's going to go that way. Does that make any sense? Behind, in front, behind, in front. Therefore, it's going to go that way. This is going to be the answer. The current's going to go to the right in this case, because it's going to go that way. What if then, though, I reverse this? Let's just say it was the opposite situation. What if I drew it where all of a sudden now this north and the south was going away from it? What would happen then? Right, I've still got my coil of wire here. What would happen then? So this is a whole separate situation. The answer was current goes to the right in this case. What if I moved it away? Then you got to think, look, Lenz's law says it's going to oppose the motion. It's going to say, it's like it's saying, come back. I was just kidding. I don't want you to leave. So if a north is going away, it's going to temporarily make a south here and a north here because it wants to oppose the north going away from it. See, in this case, it wanted to oppose the north coming towards it. One of my students like, yeah, that's like my girlfriend or boyfriend, you know, it's anytime I want to do something, they always want to do the opposite. Ha ha ha, it's not the same. But there you go, I guess it's an analogy. Was that a metaphor or a simile? I'm not that good with English. That's why I like physics. There's a lot of really straight rules for me, at least. So anyway, we look at this. We've got a north going away, and it wants to make a south then, because it wants to oppose the motion. Then you have to use your hand rule again. In this case right here, though, my thumb would be to the left, because that's the way of that one. So I put my thumb to the left, my fingers now are curling sort of like this way. So can you see my fingers have to curl from in front, then behind, then in front, then behind. So does that make any sense? In this case here, the current will be that way. Now, why is this important? This is only, I don't know, like how we get almost all electricity in the world. That's only that important. So this is really huge. Think about this. This is how we actually generate electricity. Because what you have to do is, imagine you have a wheel that's turning, and there's lots of ways of doing that. I talked about that in topic 8. There's lots of ways of turning a wheel. It could be hydroelectric. You have water passing through a pipe. That turns a water wheel. Attached to that wheel, some magnets. It could be nuclear power, right? Where you actually have this nuclear energy being converted to thermal energy, which is being used to heat up water to make steam. The steam passes the little paddle wheel. That wheel has magnets. Wind energy, same thing, right? The wind hits the blades on the wind turbine. What does it do? It imparts a momentum that way. Newton's third law says it's going to move. That rotates a wheel. Guess what's attached to the wheel? A big surprise, magnets. That's why I say it's not aliens, but it's aliens. No, it's actually magnets. You have to have moving magnets. Even on my crappy bike. On my own bike, this is what I have. I have a little light that's attached to the front fork of my bike. That thing has a little circuit in it, and it just has a little light bulb. There's no battery. And what do I attach to my wheel? Magnets, because I'm the energy source. And as I bike, I've got little magnets going around, and they basically pass around. And what really happens is this then. As a magnet is coming towards it. So just imagine then, I'm just going to try to pick up this one. Can I do that? Let's just see if I can do that. Here we go. So I've got this thing. Imagine as it's coming towards it, it's going to make, so as a magnet, because remember, the magnet's going to be going around in a wheel like this here, right? So as the magnet comes towards it, it's a wheel, right? So as it goes around like this, as it's coming towards, it'll do a situation like here where the current will be to the right. But as it goes away, notice it's going to want to oppose the motion. So that's what it's going to do like this. So during this part, when it goes away, it'll make the current go to the left. And as it comes towards it again, the current's going to switch and go to the left, then to the right, then to the left, then to the right, then to the left, and to the right. So as you have moving wheels like this, you induce electricity, true, you induce an EMF, but the important thing is you induce it in such a way that it reverses direction, because we're using moving magnets, and the magnets come towards and away because they're on a wheel. Does this maybe explain to you why then we have what's called AC, or alternating current? That's because when we have these wheels turning around and moving around, the current's always flipping direction, because you have a north coming towards it, then it does one thing. When the north goes away from it, it says, hey, come back. It does another thing. So the current's constantly flipping direction. That's what we call alternating current, AC. And this is the process. This is why we get AC as our electricity, because that's how we generate it for the most part. Other than batteries and a few other exceptions like solar power, we pretty much always get AC, alternating current. Is that amazing? So this explains like everything. Now, I've got another example for you. You have a metal rod and it's sitting on some wire. So like this is the metal rod right here, and it's free to move around. So this metal rod right here can slide, and it's sliding to the left. See that? I've drawn a little velocity vector here, or velocity arrow. We got the magnetic field B is directed into the page. That means they're going, in this case, that way into the page. In which way will the induced current flow? And this sounds really weird, but again, you want to oppose the motion of this rod going left. Now we can't use hand rule number 2 like we did before with the solenoid. There's no solenoid here. I want to oppose the motion of something moving to the left. And I've got a magnetic field. I've got a velocity, and I need a current. So if you remember from topic 5, I showed you this. This is hand rule number 3. So I'm going to show you the Star Wars way. Okay, so you're going to get out your hands like this and say, which hand rule do I need? Well, I've got a current, so I've got to use the right hand rule. It's not a left hand rule, I've got a right hand rule. Now, watch very carefully. We want to oppose the motion of this rod moving left. So that means I can take my hand, I want to make my hand, my palm to the right. Why does my palm have to be right? To oppose the motion. This is the key thing. So because the rod wants to move to the left, my palm, which is the force, must be to the right. Now, of course, I point my fingertips. Let's see, those go with the direction of the magnetic field line. So in this case here, they're going to go into the page. Does that make any sense like this? So my palm is to the right, my fingertips are inside, like going into the page, and my thumb points in the direction of either the current or the velocity. In this case right here, it's a current because it's a wire. So in this case here, this is the direction of the current, goes down. Did that make sense? That's why the current then will be, whoa. What about down here? I don't want to wreck that. The current then goes this way. That's it. So in other words, and of course it's going to go then that way. It's going to have to go around in a circle. So it'll go this way. It's going to induce a current going that way. So in this case, in the rod, it's going to go down, but the rest of it's going to go kind of that way. It's going to actually induce this current. And again, just to remind you, why is it? It's because the rod was sliding to the left. And Lenz's law says you want to oppose the motion. And in this sense, the way to oppose a rod sliding left is to make a force going to the right. So that's why I take my trusty right hand, and I had to force my palm, which is the force, to be right. And then my fingers end up being the magnetic field lines, and my thumb is the current. So that's why my thumb goes down. That's why it's down here. And because it's down here, well, that's the only way to complete the circuit, is to go around like that. That's why it does that. Awesome, huh? Let's talk about alternating current, or AC. I like that picture there where you can see Tesla and Edison are sort of on the AC versus DC side, right? AC is alternating current, DC is direct current, like you get from a battery. So the current generated, remember we've been talking about induced currents, right? Well, induced potential difference, but of course that means you get a current. And now the current, it alternates in direction because of Lenz's law and Faraday's law. We were looking at that, actually, how it'll switch direction all the time, which means when we generate electricity, it's going to be generated in an alternating manner. So that's why if we did a graph of the power, remember power is just the current times the voltage, the potential difference. So if we did a graph of the power, for example, as a function of time, it would do something like, some sort of sinusoidal function, something like this right here. And it would just sort of continue on forever. So if we looked at this then, we could actually make two different distinctions here. We can look at the maximum here that it reaches. Because here's the problem. The power itself goes up and down with time. It's not constant. And this is an issue, isn't it? I mean, if you're going to try to get something from it, you need to know what you're actually getting. So we're going to consider the average, so the sort of the middle part right here. I'm trying to draw straight lines. They're not very straight, but I think you'll get the idea. So we're going to define something called P0 or P max, which is the maximum power. So that's P max. Did you ever see an episode of Simpsons? Actually, it's an old episode where actually Homer Simpson, he changed his name to Max Power, actually. Of course, everything went really well for him when he changed his name. Then we've got this one right here in the middle. We call that the average power. So that one is this one here. That's the average. So I think this is something that's actually really important. But we also have some equations from your data booklet that we can put down. So let me just write those down. So first we have the maximum power. So P max, maybe I'll put it over here actually. So I'll say P max, that's that maximum power. And remember how power is normally just the current times the potential difference? Well, in this case right here then, if it's the maximum power, it's going to be, I hope it makes sense, the maximum current times the maximum potential difference. So that'll be this equation here for the maximum power. And then if we want the average power, that's the next one we need to have here. So we have the average power. Does that make sense then? And what we'll do is we'll take the maximum right here, the maximum current and the maximum potential difference, and we'll take half of that because it's halfway there. So I'm still going to say this I0, V0, except I'll put a half in front. And that's the equation there you need for the average power. I think that's going to be really important because actually the average power, maybe just I'll label it here, this here, that's what we actually use. And this is because, I mean, we can't really, if we use the power at any given time, it's up and down. It goes to 0 and then up to a maximum value. So instead we can actually, it's like the, whoops, what we actually use. I got to spell right. So this is the really important thing here, is this average power. Now, if we look at alternating current, we've got these different variables here. So let's maybe just make sure we know the units for them. Do you remember the unit for power? I've done that joke many times, but it's watts. Maximum potential difference, that's measured in volts. Current, I hope you know, is measured in amperes. Average power is again in watts. Now, we haven't really talked very much about the maximum current and potential difference while they're here, but we can actually go a little bit further and actually do them in more detail. So we have the current itself. If you consider the current, remember the current would go up and down. I mean, it would go a little bit crazy, right? The current would be doing something like, some sort of sinusoidal function like this. The problem is the average current is 0, so that's not very useful. Just like the average potential difference is also 0. So the problem is you can't use the average current then. Does that make sense here? Like the power itself, that'll be fine. You can do that. But you can't really use the average current or the average potential difference. So this is an issue. So instead we have something called the root mean square, RMS we call it. And the good news is that we have an equation given here as well. And it just goes like this. It's really nice and easy. It's I RMS, that's the root mean square current. And it's just going to be the maximum current divided by the square root of 2. That's what we call the root mean square. So this one right here is important. And we're also going to have the same sort of thing here, except for instead of the IRMS, we're going to have VRMS. Again, it's the root mean square potential difference. So it's going to have the same format. So it's going to be V0 over square root of 2. And this is another equation that we need. And luckily, we get. So you're given this. And again, what I want to point out is this is what we can actually use. Okay, so that's the important thing here. What we actually use. So these are the usable values here. So that's we actually use the VRMS and IRMS. That's the root mean square. Then we can go a little bit further and talk about Ohm's law. If you remember how Ohm's law went, Ohm's law normally goes R equals V over I. That's how Ohm's law normally looks. So in this case right here, if we want to know the resistance here, well, it's going to be V0 over I0. Okay, because this right here, because we can't just consider the current, because the current changes all the time. We have to consider a special kind. So we can consider the maximum potential difference over the maximum current, or we can consider the VRMS over IRMS. That's also the same. Well, it's the same ratio at least. So this is important, I think. And again, this is for resistance, right? This is for our resistance. Of course, we can put in the units. This is amperes, this is volts, this is amperes. There we go. That's actually not so bad. We've got a few equations, don't we? Now let's actually do an example. I like this one because it involves a few different things here. So you have an AC power supply, so alternating current. It can generate an EMF. Remember, that's the electromotive force, which is actually a potential difference. It has a peak amplitude of 1.0 volts. Right away, before doing anything else, let's try to decode that. What does it mean to have an EMF of a peak amplitude of 1.0 volts? That's your maximum potential difference. That's 1.0 volt. That helps, I think. Average power of this. So watch. We can put average power. That's that symbol. Square root of 2 watts. All right. Now we want the root mean square current. So what we want IRMS. And again, if you're not sure about alternating current, all you have to do is know a few of those definitions, just like I showed you here. Okay, you just have to know these different letters here, what they mean. Right? So we have average power. We have an equation for that, and we have an equation for max power. We have an equation for IRMS and everything. So let's look at this. What I like to do is just consider, what are we actually looking for? Well, we want IRMS, and because we want this, then, well, it's pretty simple. I hope you see. We just have one equation for it. Well, we have a few, but one equation we could use is this one right here. IRMS is I0 over square root of 2. So let's try to do that one. So IRMS, I'll put it maybe in a different color. So IRMS equals I0 over square root of 2. Okay, well, here's the good news then. All I need to do is find I0. All right. Can I find I0? And remember, we're given average power. So then maybe the next trick is, see, we need this. See, we need I0 in order to do this. So do you see how this sort of leads you on this little chase of what you need to get? I need I0, but all I'm given is this, average power. So maybe I should find an equation for average power. So I go back and hunt for an equation for average power, and I have half I0 V0. Okay, so we'll put that down. So average power is 1/2 I0 V0. So do you notice now I can take this I0 and solve for it, like isolate for this I0? I can get this I0 by itself. It's going to be 2 times the average power. Do you see I moved the 2 up? And I can drop the V0 down, and I can replace them. Do you see this thing here, this I0? That can go into here. Because I know P, the average power, and I know V0. So do you see how now we end up with, don't know if it's very clear, but I hope so. We're just going on a little hunting trip here, and we've found everything we needed. So IRMS is just equal to, let's see, it's I0, and I0 is this mess right here, so 2 times average power divided by V0. But don't forget, we have to do I0 over square root of 2, so I'll put a square root of 2 here. See, so far this is pretty good? Now we keep going one more step. We just put in the numbers that we know. So we have 2, and what's the average power? It's square root of 2. So 2 times square root of 2 over, here we have a square root of 2, and I don't know if this looked like it, but my square root of 2 stops right here. It doesn't go with the V0. And we just leave the V0, which is just 1. See that right there? So we just have the 1 right there. So that's just 1. All right, so let's do all this. So we have the square root of 2's, they cancel out, and I end up with just that IRMS, let's see here, is equal to 2 divided by 1. So it's just 2. Now I just have to think about significant figures, probably 2.0 if I really want to be careful, amperes. And that's it. I don't know why I ended up drawing sort of sideways like this. Do you see how we can deal with AC, right? The whole point is just look at the equations and go hunting for what you need. You just have to know what each of the equations means. Once you have that, you've got it. You got it figured out here. Transformers, more than meets the eye. We're going to be talking about transformers, but not this kind like I used to play with as a kid, but these other kind of transformers. Sorry, I couldn't resist. Oh, by the way, I love this picture here. I guess I said that a lot, but that's why I put these here. In engineering, this could be in physics though too, right? In class, you do like a super simple dumb example. Homework, it's pretty complicated, and then on the exam, it's like some insane thing. So we're going to talk about transformers because they're actually really important in everyday life. We use these all the time at, well, for our own electricity needs. So the way they work is this. Remember this epsilon here? That is a potential difference. We're going to call this whole area right here the primary. That's what this one here is going to be called over here. So on the left, it's going to be the primary, just the way I've drawn it. Over here will be called the secondary. So everything over here will have a subscript S, everything over here will have a subscript P for primary and secondary. So very quickly, what I'll do is I'll just explain to you maybe how it works. What we have is in this case right here, we've got a potential difference. Remember, that's measured in volts. We've got this measured in volts. Number of turns, those don't have units. And currents, those are in amperes and amperes. So we've got a lot of different things going on here. But what's going on is this. You've got a potential difference here as an alternating current. So what that's going to do, that's going to induce a magnetic field here. So this here is going to become magnetized. And of course, because it's changing, of course, then that right there also goes to here. And then the changing magnetic field then induces a current over here. So this is sort of the way it works. So you've got sort of electricity. So this sort of electromagnetism thing, how electricity can cause magnetism and changing magnetic fields can cause electricity. I know I'm saying it very coarsely. It's really due to lenses and Faraday's laws and with the hand rules. But if you, very coarsely, you could say that it's a sort of a thing reversed, right? You've got your current that creates a magnetic field. Magnetic field changes, which induces a current. And the advantage is this, depending on how many times you turn it. Because remember Faraday's law is related to the number of turns in the coil. If you have like a few turns here and then a bunch of turns here, that's why I said if you go from small n in this case there would be a number of turns in the primary and secondary. If you go from a small n in the primary to a large n, we call it a step up. That's because it gives a larger potential difference in the secondary. In other words, you start off with something of, I don't know, 10 volts, and maybe now you have like 50 volts. It's not just free energy though. It's like, what? How does this work? the power must be the same. If you think about it, power is current times potential difference. So what happens is this: if the potential difference goes up, then the current goes down. So basically the power is constant. If you think of it this way, then you could say that the power, which is the current in the secondary times the potential difference in the secondary, is going to be the same as the current in the primary times this in the primary. Now instead, if we just wrote these as epsilons instead, I'm just trying to show you sort of where the equation comes from. Like this right here. Can you see we could actually do fractions then? We could say, all right then, or we could actually consider, for example, IS over IP. Can you see that we could actually do that? IS divided by IP. And we could say that equals EP over ES. Do you see I'm just moving them in different places. And actually this is how they go. So if we look at this equation, this just shows you where this transformer equation came from. Because the one that you get in your data booklet goes just like this. It goes P over epsilon S equals, in this case, NP over NS, which equals, and remember now the P's do opposite than the I's. In other words, this one right here goes IS over IP. Goes like this. Let me just be sure I did it right. Let me just look it up and make sure I have it right. Yes, this is how it works. So basically, given, it depends if you know the number of turns and then you want the currents, or you might know the potential differences and you want the currents, or potential differences, you want the turns. Basically, you need to be working with 2 of the 3 of these sort of fractions. And that's how you can solve them. So they're not actually that hard. The harder part from transformers is this thing that we call rectification. I mean, this is the thing, is that's why I wrote down, like, AC is fine and all, but what if you want a DC signal? In other words, right now we've got the alternating current right here, or the alternating potential difference. It goes up and down and up and down. But what if you're hoping to power something that needs a direct current, like a nice, smooth, constant current or potential difference? Then you're in trouble. Do you see that? This is not good. So we have something called rectification. So this is the circuit diagram right here for a transformer. So just so you know, what we do is we draw this lead like this with an AC. That's what this little squiggle is supposed to mean. This I always thought looked like a hand, or like, you know, like knuckles or something like that. But this is supposed to represent the coils. Then we've got this right here that represents sort of the center of the transformer, and you got other coils. So in other words, I could have redrawn this whole thing right here. I could have drawn it as just something that looks like this, right? So I could just say, just so you can see the difference here, I could have drawn it like this, you know, saying AC, and I could then draw it, you know, with these coils, and then I could put these 2 lines, and then more coils, and like this right here. There you go, and that's also AC. So this is basically my transformer. That's the circuit diagram for this transformer. I'm actually pretty impressed. I'm not usually a very good artist, but I can sort of tell what this looks like. I'm really proud of myself. I also took my time on this drawing. You can see clearly here I haven't, but you see the idea. So what we can do to rectify things, it's like wrecked him, damn near killed him. Have you ever heard that bad joke? We've got half wave rectification. Now what this means is this: we include something called a diode. Now a diode is a special device. You see the direction like this? It actually tells you something. It only lets current in one direction through. Not the band, obviously. I mean, it only lets a current in one way. So remember, this is an alternating current. That means it goes up and then down, then up and down. It's got a positive part and a negative part, right? The current goes up and down. And remember, current is part of potential difference, so we can talk about them kind of interchangeably. So what happens is this: the positive part of the current, that will go sort of through, but the negative part of the current will just be chopped. It'll just be cut. It just won't go through. And so what this will do then, if we just do it like this, and we're looking at the potential difference across some resistor A, some resistor right here. So we're looking between A and B. We've got a voltmeter sort of just plugged in between those, and we're trying to plot, okay, what does this look like? Well, we're going to see it rectified. So what I'm going to do is show you that graph here. So let's see here. What does it look like? Well, normally, I'm just going to draw like this here. So normally, it would do something like this, right? This right here would be the normal graph of the potential difference if we did it across here. So what will happen is this: it will do the positive part just like it normally would, except this part right here, you know, the part that would be negative, it just won't do it. It won't let it through. And then it'll go up again, you know, then you could say down again. I mean, we can just, there's a few different things. So, you know, we've done a few cycles here. This is one full cycle. See, this is one full cycle of the wave. One full period is this. This is 2 full periods of the wave. So what happens is this piece that would have been there, this negative part, that part that should have been down below, it just chops it. It doesn't let it through. So through this circuit, because it only lets one of the parts of the current through, so only one of the potential difference, only the positive part, it's like it's a machine that just sort of chops off the bottom of it, basically. Can you see it? It's just like this. So we would say that this thing right here is what we call rectified. What that means, then, it takes the bottom part and just kills it. So the bottom part is now 0, so there's no negative. But the problem is, I just put this down, it doesn't look very DC to me yet. I mean, DC, it should look like, like a nice straight line like this. Clearly this isn't there yet. So that's why I just want to point out, this is the difference between rectification and smoothing. So we've got this thing, it's rectified, it's half-wave rectified, and I'll explain that in a second right here, and we're going to have it, we're going to see a smoothing circuit we can do. So you can have half-wave rectification. So same thing, remember, just like we had, except now we're going to smooth it. And to smooth it, what we do, we add a capacitor to the circuit here. So we're going to add a little capacitor right here, like that. So what this does, this is really important here. What it's going to do is, here, I'll still draw this thing right here, what it would normally want to do. So this is going to be the rectification. Actually, I'm just going to draw everything as a dotted line, actually. I'll draw it like this right here, and like this, and like this, and like this. And just so we have a few of them, right? So what it's going to do is this. The current that passes through here, of course it's going to do the same thing. It's going to have it up, and it's going to try to do these little bumps, and then a bump, and then a bump. In other words, this here, this will, whoops. So it'll attempt to do this bump. What's going to happen is this. I mean, the problem back here was that with this bump right here, the problem is it drops too low. We're trying to keep the current, or the potential difference here, the voltage, we're trying to keep it from dropping too much. See, it's dropping too much. So we're trying to keep it sort of up. We're trying to sort of boost it all the time as it goes along. So what we can do is this. Instead of wasting half of the signal, remember that, the signal that, goes up and down like this, instead of wasting half of it, instead of wasting that half, what we do is we put in this capacitor. So what it does is when the current is passing through here, yes, it passes through here, but it also passes through that capacitor, and it charges the capacitor. So the capacitor is like a little mini battery. So it's going to charge up the capacitor as it goes through. And the advantage is when it doesn't have the signal, when there's the other half of the signal that's not getting through, instead of just being killed, the capacitor is then allowed to discharge and send something through this resistor. So what it does is this. It goes up, but then what happens is this. Instead of dropping all the way down, the capacitor is discharging, so it's helping out basically. So it's going to go something like, something like this. And then it'll go up again, and then down again like this. And then up again, and then down. So this is better. So this right here, why it's rectified, and it is smooth. That's why I put rectified and smoothed. So this is called a half-wave rectification. And like I said, we rectify it with a diode. We smooth it by adding a capacitor, which can then charge up while the current flows through. And then when the current stops in that diode, the capacitor, it discharges into the resistor. Now the important thing is this, it only does it one time per cycle. If you consider like one whole cycle being from here to here as one cycle, do you notice it just rectifies it and smooths it just once in a full period? So this is the advantage and disadvantage of it. It's better, certainly, than just rectifying it. Well, it's better than this, obviously. This is just nothing. That doesn't help. So it's better, and then it got even better because you smoothed it. That's called half-wave rectification. In the last video, we were talking about rectification and the idea that we're trying to smooth out and sort of make a nice DC signal from an AC. Remember, this alternating current, like this potential difference here, is not very helpful for us, especially if we want to get a nice direct current signal. So one way was to do half-wave rectification, which means in the circuit diagram you put in one diode, and that rectified it, which means it took the negative part and chopped it. And then we learned that if you add a capacitor to that little piece right there, that allows it, remember what the diode does, right? It only lets half of the potential difference or the current through. And so by doing this right here, adding the capacitor, it allows the current the capacitor to charge while there's current flowing through it. But then when the current doesn't flow through this thing right here, then it can discharge and sort of add. So this was a matter of rectifying and smoothing it. But the problem was it only does it one time per cycle. And we have something better. We can call it now full wave rectification. To do that, it looks a lot like the half wave. Remember here we had a diode right here, except what you do is you split up your coils into two and you add a diode on the bottom. So what you do is you put it like this. So can you see this one here? You put your coils, maybe half the coils over here. We call it a center tap because we put a little line right here where you can connect things. And then you end up putting another diode there. You still have that little capacitor there. So I'm going to show you this is rectified and smoothed. In other words, I already put the capacitor in there. So what this is going to allow you to do is, if you think about it, it's going to allow you to do this sort of rectifying and smoothing in one part of the cycle, but also the other part of the cycle. So it's going to take the top and the bottom parts and do it. So what this will end up looking like, it'll end up doing, let me show you here. So if we just rectified it, what it would do is it would take the top part, keep it positive. That would be this top part right here. And what would end up happening is this, when the current reverses direction, it would actually take that piece and let that piece through as well. So what it'll do is it'll put that one up above as well, and then another one, and another one, and so on. Now what ends up happening is this, the one full cycle though is actually this. So let me just show you here. One full cycle, this is the top part, this is where it would have been the bottom part, it just took it, let it through, so that's why it sort of reversed it. So this is actually one full cycle right here, and so is this. That's one cycle. See, before, one cycle was all the way up, then it was, chopped, and then all the way up again. So this was one full cycle in the half wave rectification. Now I got full wave rectification. This is still the same cycle. This would be the same time here, whatever time that was. Except now it adds like two bumps, like boing, boing. It looks like a bouncing ball or something like that. So this is what it does. It does it 2 times per cycle. Now I've put it already not just rectified but also smoothed because I've got the capacitor in there. So this time, just for fun, I showed you the rectified and smoothed one. Right now this is the curve for just rectified, not smoothed. In order to have it rectified and smoothed, which is what this really will do, because the capacitor can discharge and then charge and discharge, it'll go up, and what it'll do, of course, then the capacitor then discharges like this, and then it charges again, and then discharges, and it charges again, and discharges. I'm sort of making my eyebrows do it for some reason, I don't know why. This is much, much better. Do you see how this is a lot more direct? See this one here? It's DC-ish. I mean, it's not perfect, but it's sort of direct current-ish. I mean, it's at least a pretty constant potential difference or current. So the only problem is this. This is the sort of hard part about it, is that you need twice the number of coils to do this. So in other words, depending on how many coils you needed for half-wave rectification, the problem is you need more coils to do this. Okay, that's not necessarily a deal breaker, but this is how you can do full wave rectification by just using 2 diodes and the capacitor. So now comes the next part, the part that scares a lot of people. Full wave rectification using a diode bridge. And a lot of people look at this and go, oh, they want to throw up just like this. I love this picture. This is from Dumb and Dumber. I just love this. So this guy wants to throw up. Yeah, absolutely. Now, there is an advantage to using full wave rectification with a diode bridge. The advantage is you need less coils. So I guess if there's a real shortage on coils in the world, that's something that's an advantage. The disadvantage is you need to use lots more diodes. Well, lots, double. And the circuit looks pretty gross. So, I mean, this makes you feel like that. So here's what's going on. We have the same sort of transformer circuit before. The AC is coming into the primary. In the secondary, we still have some coils here and then a center, just to show you sort of where the center tap used to be. The issue is now we draw this thing called a diode bridge. You basically have the diodes. Can you see this one here pointing that way? So it lets things sort of up and right, and so does that one. These ones here let them down and right and down and right. You still have this sort of capacitor here. The advantage is this is going to still do the same sort of thing. It's still going to be having this thing rectified and smooth. It's going to be very much like this example over here, with the 2 diodes and the capacitor. The advantage is you need less coils to do it. So it's just another way of doing it. And the way it kind of works is that it's going to end up allowing you to rectify things on both parts of this cycle as well. So maybe just to show you a little bit how it works, I like this diagram right here. It sort of shows it more clearly. When you have the sort of positive part of the current, so to speak, you can see then the current will go sort of up and then it'll go sort of that way. And look at this then. It's got these two diodes. Those are the ones going down and right. So let's see, that'll be for you, that'll be like this. Then it allows things to go that way. So can you see what'll happen is this. It'll only allow this from here through here, right? So that'll be the load right there. And then it goes through here and then back over here. So basically it just goes like this and then goes way back in. So that sort of rectified it one way. But the advantage is that, and it also smooths it. The advantage is in the other part of the cycle, so when the cycle sort of reverses like this, watch what happens here. This time it goes like this, and instead of going through here, see that diode cuts it, doesn't allow it to go. So these ones right here, they go sort of up and right. Like both of these sort of diodes, both of them going up and right. Imagine then this current can go this way, and then it goes through that one, then through here, and then does this sort of little circuit like this. So this rectifies and smooths that piece of the circuit. So that's just why we've got this piece right here. Because remember what it was being fed. If you look at it, what's being fed to it, see this top part here and this bottom part right here? That's what we're sort of feeding it. We're kind of feeding it an AC signal. Can you see those are the top and bottom parts of this one here? Can you see that's here and here? We're sort of feeding it an AC signal here. We're giving it AC, you know, across this and across this. So that's why, see, we just feed it an AC signal here, and it basically rectifies and smooths it itself through this really clever arrangement of diodes. So maybe then you don't quite feel like throwing up as much. Now I've got an example for you. So let's do this. Let's sketch a graph of the potential difference versus time across these points A and B. So think very carefully. Is this full wave rectification or is this half wave rectification? Oh, wait a second. I need to go back here and show you something else. Whoops. The advantage was here, I just want to point this out. The advantage was you do this 2 times per cycle. In other words, you get to rectify and smooth 2 times in a cycle. That's why it's called full wave. I don't know why I didn't say that before. That's really important. This here is really important. So if your cycle was, I don't know, let's say like 5 milliseconds, then you do it twice. It happens 2 times within that 5 milliseconds. Whereas the half wave rectification, let's say this was 5 milliseconds, it only smooths it once. So that's sort of an advantage. Sorry about that. Now let's go back and look at this example. We want to sketch a graph of the potential difference versus time across points A and B. So again, we're going to do this sort of sketch like this if we can. Let's see here. I'll draw like this. And I'm going to line the line. Yeah, sure, like this. And I'm going to label this time in seconds. And I'm going to label this the potential difference, which will be in volts. So let's take a look at what this will look like. What kind of rectification circuit is this? Is this full wave or half wave? You know it's going to be full wave. Do you know why you know it's full wave? 2 diodes. That's how. Because you have 2 diodes. If you had 1 diode, it would have been half wave. Look back here. The half wave rectification only used 1 diode. In order to have 2 diodes going on right here, can you see it's one of these? But do you notice we don't have the capacitor plugged in? Look at the circuit that I gave you. It looks just like this here without the capacitor. Look, here's the example. We don't have a capacitor here. So do you notice we're going to be doing rectification, but we're not going to do smoothing. Do you know why no smoothing? Because you needed the capacitor to do the smoothing, in order to allow that capacitor to discharge and do the smoothing. So we're going to do rectification, but not smoothing. So in this case here, let's take a look then. What will that look like? And it's going to be full wave because you've got 1 diode here and 1 diode here. So if we put the voltmeter across these points A and B, we're going to end up with something that's going to look like, let's see here. It's going to look like, it's going to want to go like this right here and like this. Actually, never mind. It doesn't have to be dotted line. It'll be solid line. It'll be like this. So it'll go like this. So it'll be up and down and up and down and up and down like this. This will be rectified but not smoothed. And remember, if you really want to be careful, I think it's sometimes a good idea to show where your 1 period is. This is 1 full cycle. So in other words, it does it 2 times. It has 2 sort of bumps here per cycle. So that's the important thing here. I think it's just important to know what these drawings will look like. So that was, it was rectified but not smoothed. See over here, we had the one that was rectified and smoothed. So that's just the difference. So I hope this helps you out. I hope this makes more sense and you don't feel like throwing up quite as much at least. I'm going to speak to you now about capacitance, both in series and in parallel. I like this dog, you know, I have no idea what I'm doing. I think a lot of people think this way about capacitors, but if you think of them as like a mini battery, I think it's a pretty effective way to think about it. So that's because a little capacitor, it can charge and it can discharge in a circuit. So you can actually charge it up and then you can actually discharge it. So it kind of acts like a battery, except it discharges pretty fast. But we have this thing called capacitance. And that's a property here. And you're actually given this equation on your formula booklet. So it goes C equals Q over V. This is the equation you get. So this one here tells you this. We have the capacitance, which is a new thing we're measuring. It's a new quantity. It's measured in what's called farad after Faraday. Keep in mind though, the capacitance unit, like 1 farad, is actually very, very large, which means when you're looking at real capacitors, they tend to have very, very small versions of this. So in other words, don't be surprised if you get like microfarads or nanofarads or things like that. So very, very small amounts of farad, because 1 farad is actually a huge amount. Of course, we have charge, and charge is measured in coulombs, and we have potential difference, which is in volts. So this is your equation here. That's about it, really. Just Q over V. So if we look at a parallel plate capacitor, I mean, we tend to actually, I mean, the actual circuit diagram looks like this. That's the one where you have these two parallel lines that are the same length. Remember, if there's one really short, one really long, that's the battery, right? So that would be this right here. But in this case, a parallel plate capacitor, I'm actually trying to show you the real thing here. Here's what it would look like, you know, sort of seen sort of from the side. That's my attempt, at least, at doing that. So you've got these parallel plate capacitor with A. There's a surface area A. So there's an area of each plate. That would be in meters squared. You have your capacitance, which is again in farads. You have something called permittivity. Now, this thing, where we use this Greek symbol epsilon. Epsilon 0 is the permittivity of free space. You can look that up. That's if you put like air or vacuum or something in the middle here. But what we can do is, oh, by the way, I'll talk about that in a second, actually. I just don't want to get ahead of myself. We have the distance separation between the plates. That's in meters. This is just a constant you can look up, at least for epsilon 0. But each different material has its own permittivity. And so what we can do is we can add things inside, like, you know, between a parallel plate capacitor. For example, we can add something called a dielectric. And what that does, it'll be a material then whose, I mean, you have to look up its permittivity. It might be something different. But its goal, the reason why we add dielectrics is to increase the capacitance. We want to increase, you know, what the charge per volt that it can sort of store, you could say. So what it does, it reduces the potential difference between them. And imagine this, if you reduce this, if you make V smaller, does it make sense then that C will get bigger? Because if you divide by a smaller number, your answer is actually larger. So that's why it reduces V, but the goal is to increase C. So that's the point of a dielectric. That's about it really for capacitors. So you'll see it's actually not nearly as bad as it seems. The equations might seem a little bit wacky, but I promise you they're not so bad. We've got series capacitors, which means if we have a battery or a cell and we put in 3 capacitors in series, you might think, oh, I remember how that goes. It's like a resistance where the effective resistance is going to be just add them all up. But capacitors work in the opposite way that you think. So luckily you have this equation as well, 1 over C, and it says series. Like this, they work like resistors in parallel. In other words, it goes 1 over C1 plus 1 over C2 plus 1 over C3 plus dot, dot, dot. So this is the equation. And luckily, you don't have to memorize this. This is given. So this is on your data booklet. So this is really nice. So again, it just works a little bit like parallel resistors is how you deal with series capacitors. And conversely, if we have parallel capacitors where things here have a choice where they can go, we also have an equation for that, and it says, so again, it goes opposite. So you'd think that C in parallel should be the complicated one with the 1 over whatever stuff. Nope, that's the easy one. That's where you just add them up. So you just add them up until you have all the capacitors dealt with. And these are your equations that you get. I mean, they're on your data booklet. You don't have to memorize them. Now comes what I think is maybe a too simplistic example, but it's just to get you practice here. So we have 3 capacitors. So we have 5 microfarads, 10 microfarads, and 20 microfarads. And they're all connected in series. What's the combined capacitance? In other words, what's the effective capacitance? So what you could do, of course, you put them all in series, right? You have one, then another. Oops, not resistors, sorry. Ooh, that was bad of me. Capacitors. There we go. This one here is 5 microfarads. This one's 10, and this one's 20. And so what you do, of course, you'd use this idea, right? That 1 over, so maybe we'll use that equation. The 1 over C in series. How do we use it? We say it's 1 over 5. Keep in mind, since they're all microfarads, I can actually be lazy and just say 1 over 5 plus 1 over 10 plus 1 over 20. And of course, then that gives you your C in series. Then, you add these up and then you do 1 over that. Let's assume this is on paper 2, so something like this. So I can just do 1/5 plus 1/10 plus 1/20. And I do 1 over that answer. And I end up with 2 point... On this right here, ooh, I should have been careful. I should have said 5.0, shouldn't I? Something like that. So let's say it's 2.9 times 10 to the, well, we could say microfarads. It's going to be the same unit that we just had. So it's going to be microfarads. That's it. That's how we can do it. I mean, keep in mind what we can do, right? What if, actually, I'm really not very satisfied with that example. Let's do a better one. So I'll just make one up here. So this is something that you might see on a circuit diagram. You might easily see something like this. What if I see when it goes like this, and then this is in parallel to this. Something like this. I say, now what's the equivalent? So here I could say C1 and C2 and C3, let's just say. And let's give these here values. Actually, no, I shouldn't call them that. I should actually give them values. So let's just say it's 5 microfarads. We'll keep it 10 microfarads, and this one here will be 20, just like we had before. Let's just figure that out instead. I think that's maybe more useful to see what happens when you have a series and parallel, sort of a combination. Well, normally, what I would do is redraw the series one. So I would make this right here simpler by just drawing this right here. In other words, what's the equivalent? I'm trying to draw this and figure out what happens in series. So these two things are here in series. I'll say 1 over C in series of just this top part is going to be 1 over 5 plus 1 over 10. And 1 over 5 plus 1 over 10, let's see, that's going to be, that's the same thing as saying 2 over 10. That's the same thing as 1 over 5. So then I have 3 over 10. Then I have 10 over 3 is my answer for, I should be very, very careful actually. I should say this is technically 3 over 10. And then I could say therefore that this value right here then is not going to be 3 over 10. It's going to be 10 over 3. Let's maybe just do it the actual values here. So we'll do 10 over 3. So this is 3.33 microfarads. That's the equivalent now. That's because that was 1 over CS and I wanted CS by itself. So that's this value. Now I've redrawn this as this and this is 20. And then what do I do now? Now I can redraw it as just one capacitor because now I have them in parallel. And remember what we do for parallel? We do C in parallel is just equal to the two numbers added together. So it's 3.33 plus 20. So that will give me, let's see, 23.33 microfarads. Now if I wanted to keep this 5.0, with two significant figures everywhere, then I can say fine, it's basically this ends up being 23 microfarads. So you could say that is the same thing. So that's, if I drew it as just one capacitor. Maybe that's more useful to have shown you a parallel and series one. Because things like this can show up often on exams, and I just want to make sure you're ready for all the different kind of things that they could throw at you. So now we've got capacitors ready. Now let's look at what happens when we charge them and discharge them. That's coming in the next video. So with capacitors, we can also look at what happens when they charge and discharge. And I like this meme raccoon here saying that, they tried to teach me about capacitance, but I resisted. So let's look at discharging capacitors. What happens then is as they discharge, so that means that assuming that a capacitor is already charged, basically, so let's assume it's acting like a little battery, it's charged up, we've got a resistor there, and what we do is we take that switch and we close it. So when you close the switch, it'll discharge. And the charge in the capacitor will work like this. Here's the equation it's going to use. So it's going to sort of follow this. Let's look at this. So we've got Q, that's the charge remaining after some certain time. We got Q0 is the initial charge. So that's in coulombs as well. Time elapsed will be in seconds usually. Time constant, we're going to see that right there, what kind of unit it has, but it's kind of like a unit of time. Resistance is in ohms and capacitance is in farads. So let's look carefully at this one right here. What it does, it's an exponential curve and it's a negative exponential. So hopefully you remember, it goes just like what radioactivity does. It sort of goes like this. Something like that. Of course it goes down to almost zero charge. So it's sort of asymptotic like this. That's okay, that shouldn't be too hard. I mean, we've got this weird thing called tau right here. This is this time constant, and we define it as R times C. So this is just a little piece right here. So you could say it's T over RC if you want, and that would be fine too. Now let's look at this. What happens to the current and the potential difference during the discharge? So while it discharges, we have both the current and the PD, because of course it's discharging, so we can look at this. So we have the current itself, and I hope it'll make sense then during the discharge that the current is going to go like this. So same sort of equation here. So it's also going to go like this. The potential difference will also go like this. That's of course while it discharges. But what I want to show you is what happens when it charges. So this is during charging. So this is where you're actually, charging up a capacitor. What's interesting, I mean, it should hopefully make sense that the potential difference will go up, but of course it becomes asymptotic because at some point it's actually fully charged, which means then there's no more current that will flow. And that's because it's got all the potential difference at once. What's kind of weird or counterintuitive is that while it's charging, the current still does this. That's actually because, like I said, once it's charged, then the current stops flowing. So that means once it's charged, the current stops flowing. It's a bit counterintuitive, this one. That's why I want to point that out. Okay, so while discharging, the current drops down like this. Well, while charging, it also does that. Potential difference, however, while discharging goes down and while charging goes up. So it's like the potential difference or the voltage is the one that sort of makes sense. It's the one that works the way it should. It's the current that's a little bit wacky. So do keep that in mind. This right here is this is important. Now we have the energy that can be stored in a capacitor, and it's just CV squared, where E is the energy stored, and energy stored, guess what unit that has? Joules. We've got capacitance, which is still in farads. We've got potential difference, which is in volts. So this is just a half CV squared, and you get this equation on your data booklet. There's not really much to do about it other than there it is. Use it if you have C and E and you want V, for example, or something like that. If you know two of these three, then you can find the other one. I think more interesting then is just to look at some IB questions. So I like this one here. In the circuit below, capacitor C is charged through a resistor R. See that? So it's charged through this. Draw the graph of the potential difference versus time and the current versus time when the switch is closed. So we're told it's already charged, which means now when it's closed, guess what happens? Now it's going to discharge. So all you have to do for this is just remember, what does the graph of a discharging V look like? The potential difference goes down, and so does the current. And that's all we needed. That's that question. So that was actually really easy. I was just asking what we had before. Now comes maybe a more interesting one. I like this one a lot better. So in the following circuit, we have a capacitor. It's initially uncharged. Okay, so we start off with this little capacitor right here. We're going to say it's uncharged. It doesn't have any charge in it. It's got a capacitance, but it doesn't have any Q in it. No charge yet. Now the battery has a negligible internal resistance. That's good. That means it makes it a lot simpler to work with. We have a battery here at 12.0 volts. So now what we do is we close switch 1. So you can imagine now this one here is closed now. It goes like this. When this is closed, what happens? Actually, maybe I won't draw like that. I'll leave it like this. When this here is closed, can you see we're going to complete the circuit this way or this way? So we're going to complete that circuit. So what happens then? It's going to charge. Okay, so this is important. The capacitor, it charges. So do a sketch of the potential difference versus time. Boy, have we seen this before? They love to ask about this, don't they? So we'll have time and we'll have a potential difference in volts, and this will be in seconds. What happens while it charges? We have to remember that graph, but it goes up like it should, like this. The current is the one that's weird while it charges. So it makes sense. The potential difference goes up. Now what do? We open that switch. So basically we stop basically this one here from happening. We open it like this. And now we close 2. Does that make sense that now it's going to discharge? That's the thing. See, the capacitor will discharge now. So this is the important thing, right? Because now it's charged, right? We close this, it's all fully charged. And now what we do is we open this and we close this. So now it can discharge. So what will be the drop in potential difference in the capacitor after this many seconds? So I think it's important to maybe just to try to look at what's the equation that we need for the potential difference. We have an equation for it, right? It's this one. Potential difference is V0 e to the minus t over tau. Maybe we just need to find all these things and we can start plugging them in. So this is going to be the potential difference after 7.1 milliseconds. Let's be very careful with the values we know, okay? Let's be very careful. We know that time, it's not just 7.1 seconds, it's 7.1 milliseconds. You have to be really careful with these. This is where you can make a mistake because it looks like a meter second. And this is the IB's most common thing that they like to do is to put MS because it looks like meter seconds. Like, aha, we're trying to trick you. So don't get tricked by that. It's a millisecond, so it's 10 to the minus 3 seconds. Do we know R? We sure do. It's 7,900 ohms. Do we know C? We sure do. It's 5 times 10. And remember what micro means? Times 10 to the minus 6. Farads. So we have these values right here. So what do we put in here? Do you see how we can actually figure this all out? We know the initial amount, by the way, because what happened? It fully charged. So do we know what the potential difference across that capacitor was? We sure do. It was actually 12 because this was 12. So we can say this one here is 12. Therefore, we put this all in here. Let's see if we can do it. So we have V equals, let's see, 12 times E to the power of negative, let's say it's 7.1 times 10 to the minus 3. All that divided by tau. Remember, tau is R times C. So we have to put in 7,900 times C, which is 5 times 10 to the minus 6. Phew, let's see if that works. So I'm going to start over the bottom, maybe just to make it easier. So 5 times 10 to the minus 6. I'm going to do that times 7,900. I'm going to say in brackets 7.1 times 10 to the minus 3 divided by that answer. I'm going to take e to the negative that answer. And I'm going to take that times 12. And I end up with something like V equals 10.02, but I'm only allowed 2 significant figures. Is that true? Yeah. Yeah, I'm only allowed 2 significant figures. So I'll just say 10. And what's the units here? It should be actually just 10 volts. So this is your answer, right? Nope. Look very, very carefully. This is the potential difference in the capacitor after this many seconds. This is what it will be. However, they didn't ask what is the potential difference in the capacitor. They said, watch very carefully, this is why it's a sneaky question. What's the drop? So this is the potential difference after 7.1 seconds. The problem is that's not the drop. The drop is equal to the original amount that it started off with. It started off with 12 when it was charged. So it's 12 minus 10, so that equals 2.0 volts. Sneaky, sneaky IB. And then finally, we got to calculate the charge that flows in the circuit during that time. Maybe a good way to do that is just use this equation of C equals Q over V. I think that's maybe the simplest version to use. And therefore, we can say Q then equals CV. Now keep in mind, during this right here, we have 2 different amounts of charge. I mean, we need to find basically the difference in charge. That's the amount of charge that flowed. So I think it's important to do maybe Q initial. We'll figure that out. Maybe I'll do this over here. I'll bring it to the left side maybe. We'll do it down here. We'll have Q initial and we'll have Q final. Maybe that's going to be simpler like this. So I'll have Q final. So Q initial will be the initial C, which is 5 times 10 to the minus 6, So 5 times 10 to the minus 6 times V initial, which is 12. Now the final amount, we need to find out this, right? We need to find out what the final capacitor's value will be after this right here. So how do we actually figure that out? Well, I mean, we know the capacitance, it's still 5. Actually, that doesn't change. The value that changed is actually this number right here, this V. Because the potential difference, final, is not 12, it's now 10. So we can still use that answer of 10 that we had before. So this is what we're going to be calculating, these two values here. So we'll do 5 times 10 to the minus 6 times 12. So just in case you want to do all this here, you can do it like this. There we get 6 times 10 to the minus 5 coulombs. And of course, if we have 5 times 10 to the minus 6 times 10, that just multiplies it by 10, which means it goes 1 less. So this is 5 times 10 to the minus 5 coulombs. And the charge that flows will be a delta Q. That'll be the flowing charge. It'll just be the one minus the other. So 6 times 10 to the minus 5 minus 5 times 10 to the minus 5, which is 1. Now we're supposed to have two significant figures, so I'll say 1.0 times 10 to the minus 5 coulombs. There we go. So that is our final answer. So we've dealt with capacitors, and hopefully you haven't reached your capacity for these kind of questions. But there we go. We're done with that bad pun. Sorry. In this video, I'm going to show you about energy levels and quantized energy. I think first it's important to just talk about this whole idea about quantum mechanics. People use this word to invoke some sort of mystery to something, like, oh, it's quantum mechanics, it's really tough. I mean, yes, understanding it's a little bit weird, but the basic idea of it is really pretty simple. If something is quantized, it just means something comes in certain amounts. For example, students in a class are quantized because they only come in, discrete amounts, 1, 2, 3, 4, whatever, 5 students. You can't have like half of a student. Well, I guess you can, it's sort of messy. But I mean, if you want to consider quantized things, it's just things that come in certain countable amounts. So for example, what we find out is that energy of a photon is quantized, which means the energy of one little piece of light, basically, that comes in only certain amounts. So this is actually something that's really important here. Oh, by the way, I put this picture right here of quantum mechanics because it reminded me of, it's almost like it's a pun, obviously. It's like a mechanic who's working on an atom. It's like the broken atom, so they're trying to work on it like it's a car. But let's talk about energy levels. So what we have is this process. This actually happens in your own classroom, perhaps, where you're sitting, where, if you look up and you have fluorescent light there, some sort of fluorescent light, what's happening is you're applying a potential difference to some atoms in a gas usually, and those atoms, the electrons in those atoms get excited. And when they get excited, they go up in energy level, just like what I'm going to be showing you here. And every time an electron goes up in energy level, that means eventually it'll probably come down. And if it comes down in energy level, this is the key thing, when it goes back down, it emits a photon, which is one piece of light. And it's got a very specific energy. This is the whole thing, is that energy is equal to HF. So I think it would help maybe if I just define this. So E is the energy, and this could be in electron volts or it could be in joules. H is just a constant. You can actually look it up. It's called Planck's constant, even though it's named H. And it's 6.63 times 10 to the minus 34. And then we've got, let's see here, frequency, which is measured in hertz, or 1/seconds. So this is the whole idea here, is the very fact that specific energy levels are possible, that means that specific photon energies are possible. And what I'll explain to you is this. See, this is actually coming from the Bohr theory of the atom, that there's only certain orbits that are possible. And so what you can look at is this. You can look at these different energy levels. It means that not everything is possible. This electron cannot be somewhere in the middle. It basically starts off, it's basically way up high, and then it has to drop down, and then drop down, and then drop down. So it can't just do something halfway. It's either right here, or it's the next one, or it's the next one down. It can't be anywhere in the middle. So let's say, for example, we have an electron, gets excited, and don't worry too much about negatives as far as energy levels go. Don't worry about that. That's just a weird thing about, you have to have the infinitieth orbit that gives you an energy of 0. So let's just assume, something goes up like this right here. What'll happen is, when it drops down in energy, which will invariably happen, so let's just say it drops down, let's say, to this one. Every time it does that little drop, anytime a photon goes down in energy, it's going to emit a photon. And that photon will have a very specific energy. Do you see, if you can figure out what's that energy difference here, what's this delta E here, what's that energy difference? That is going to be equal to HF, where H is that constant, and F is the frequency of the light. So essentially it tells you the color of the light. So what's really important is this: the very fact that there's different energy levels possible, that means that there's specific photon energies possible. And this is why we say this is quantized. We say it's quantized because the energy only comes in countable amounts. Look, right? The energy comes in 1 times F or 1 times H or 2 times H or whatever. So it's always a multiple of H. So for example, this one right here, it'll also have another transition possible. Maybe it from there drops down to here, and then it drops down. Or maybe it goes all the way down in one go. You can see how these are all different photons. Each of these photons, you see the energy difference. The energy, from the bottom to the top is different. Because of that, it'll have a different color. This explains why in your own, let's say if there's a fluorescent light above you, that explains why there's only specific colors. You could take that light, for example, put it into a spectrum, so put it through like a prism or a diffraction grating or something, and actually break it up into its component parts. You'd end up seeing what that light was made of, because there's only going to be specific wavelengths possible. Right? Because there's only these certain amount of transitions. In this case, I've drawn this as 1, 2, 3. There should be 4 different photons that I can see. That means there's going to be 4 different individual frequencies or wavelengths that you can see. Right? Because frequency is just like wavelength. So I think that is something really, really important about quantum mechanics, is that things can be quantized. In this case, energy is. Energy comes in countable amounts or multiples of this magical number H. So now I've got an example for you. So we have electrons in an atom, and in this case right here, I think I chose, that looks like the energy levels for hydrogen. So we have electrons in a hydrogen atom, and they're excited. What I mean by that means they go up in energy level. And they have the following energy levels possible. So they tell you this in electron volts. First of all, how many different photons are possible? So what that means, I think it's maybe a good idea to try to just count them. So from here, how many different ways are there to go down in some way? What I like to do is be methodical. From here, you can go all the way down. You could go down by 2 or down by 1. Then once you're here, you could go down by 2 or down by 1. And once you're down here, you can only go this one. So it turns out these are all the different transitions possible. How many are there? There's 1, 2, 3, 4, 5, 6. So the answer here is 6. You see? So that just tells us there's going to be 6 different photons going on here. Now, what's the smallest wavelength of a photon that could be emitted? Now, you got to think a little bit about wavelength here. What letter is that? Do you remember? It's lambda. Now, the only equation we have to work with is E equals hf. So tell me about this. How is lambda related to f? Do you remember this? We have an equation, C equals f lambda, that tells us the speed of light is equal to the frequency of the light times the wavelength. So if I wanted to get wavelength by itself, what would I do then? Well, actually, no, let's maybe take a look at this. Yeah, it'll be okay. So E equals h, and instead of f, what can I do? I can say f equals, in this case, c over lambda. Because in this case, can you see, I can just get f by itself, so I divide the c by lambda, so there we go. And that means every time I see an f, I can replace it with c over lambda. In this case, it's supposed to be hf, it's going to be hc over lambda. So what this tells us in a way is this: we have this equation or we have this equation. If we want the smallest wavelength, I just want to talk to you about it a little bit qualitatively. So smallest lambda. Do you notice, by the way, the frequency and the wavelengths kind of work opposites? Like a large frequency is going to be a small wavelength. And if you remember this idea, this is really going to help here. Because the smallest lambda is going to correspond to the largest. We want the largest frequency. Smallest lambda is largest frequency. And since E equals hf, does it make sense? If we want the largest frequency, then we want the largest energy. This is going to be the important thing. So we want the largest energy then. Does that make sense how we figured that out? So again, we want the smallest wavelength. And if we remember that wavelength and frequency are kind of opposites, in that, if one goes down, the other goes up, then smallest wavelength means largest frequency. And because energy is directly proportional to the frequency, that means that largest frequency will be the largest energy. So then take a look at these different photons here. Which one is the largest energy difference? I hope it's clear. It's from here to here. It's this one right here. This is my magical one that's going to help, right? That's the largest energy difference. So then let's maybe find the energy difference. Well, it's going to be minus 0.85 minus, what is that, minus 13.6. What does that give me? That's 12.75. Yeah. Technically it's a negative, but the idea is we just want the absolute value of it. So we can say it's this many. Of course, it's electron volts. Now, this is great because now I have an energy. But maybe it helps to convert it from electron volts to actual real units that I can use. So do you remember the conversion factor for electron volts? I want to put EV on the bottom so I cancel them out. I need to know something per EV. And it turns out I know that 1.6 times 10 to the minus 19 joules is 1 EV. If you don't remember how to do that, remember just take, that's 1 times the charge of an electron, which is 1.6 times 10 to the minus 19 coulombs. Multiply that by 1 volt, and it turns out a coulomb volt equals a joule. So I've just shown you again the derivation for what 1 EV is. So just so you know, you use that right here. So then I take my 12.75, let's see here, 12.75. I multiply that by the charge of an electron, because that tells me how many joules are in an EV, and I end up with my delta energy is 2.04 times 10 to the minus 18 joules. Why do I use this? This is because now what I can do, I can actually find now the wavelength. That's because I can use this equation E equals hc over lambda. So I know that this thing here equals hc over lambda. Therefore, I know that lambda equals h, which is going to be 6.63 times 10 to the minus 34. You just look that up. Times c, which is the speed of light, 3 times 10 to the 8 meters per second. I divide that by my delta E in joules, so that's going to be 2.04 times 10 to the minus 18. And let's see what we get. 6.63 times C. Divide that by 2.04 times 10 to the minus 18. And I get a value of 9.75 times 10 to the minus 8 meters. So if I want to do it to two significant figures, that would be 9.8 times 10 to the minus 8 meters. Or if you really want, you could say it's 98 nanometers, I guess you could say. So but they're both okay. You could say this one, or you can say it's 98 nanometers. Basically, it tells you it's really small. Remember, if you think about what we can see, the human eye, we can only see things around 400-ish nanometers. That's what we can detect. So you probably wouldn't be able to detect this with your human eye, but you could use some other detectors to detect this. So we can use devices to help us with this. So do you see how this quantum mechanics kind of works? The fact that these energy levels, there's only certain ones possible, that's what leads to the fact that only certain photon energies are possible. So that's why the energy of a photon, E equals hf, is quantized, because it's always a multiple of this magical h value. So see, quantum mechanics doesn't have to be so hard. Photoelectric effect is something that shows up a lot on exams, and the good news is it's not actually that hard. I like this joke here from Science Cat here. A photon checks into a hotel and is asked if he needs any help with his luggage. No thanks, I'm traveling light. Ha. So let's talk about photons themselves. So what they are, they're little pieces of light, right? It's a little sort of particle of light. And if you have a photon, it's incident on a metal surface. So for example, it could be something like zinc. So let's say here we have a little metal here. And what I'm going to do is have a photon coming in. I'm going to use a proper sort of Feynman diagram notation, use a squiggly line here. Here's your photon coming in. Now, it's going to come into this zinc here, and under certain conditions, which we're going to talk about, you could have electrons ejected. This is what happens here. They're emitted. We call them photoelectrons for a reason, right? Because they're electrons that came from photons. So photons caused electrons to come out. That's why I like the term photoelectric effect. The definition is in the name. Photo means light, electric means electron. So you have a photoelectron. That's how you know it's light and electricity. Now there's features of it. So this is what's really interesting about it. How's this? I'll show you this. Remember this equation, E equals hf. That the energy of light, for example, should be dependent on the frequency. So it made sense to a lot of people at the time, this is in the early 1900s, that if you had this effect right here happening, that, you know, these electrons should also be given that energy. In other words, if you had a photon coming in with a certain energy, E equals hf, it should make sense then that those electrons would have that same energy, or at least very similar. Certainly it should go in the same way. They fully expected this graph to be linear. They expected to do something like this. In other words, you know, at no frequency, well, then there's no energy, so then there should be no energy out. And as larger frequencies, it should have larger energies of electrons, because it was able to impart its energy to those electrons. The problem is, this is not what happens. What really happens is this is what really confused people. There exists a threshold frequency below which nothing will happen. In other words, no electrons will be emitted. So maybe it goes something like that, let's just say. So then this right here would be this magical value here. This frequency, if there's some value right here, we're going to call it F0. That's called the threshold frequency. What's really weird is this. Remember, it depends on the energy of your photons. So if you have photons with less energy than that, so in other words, different colored photons, remember, less energy means less frequency. That means greater wavelength. So if you have photons with a greater wavelength, they have less energy. And at some point, you get to where nothing happens. No photoelectric effect happens. And this was absolutely confusing. Because why should there be this threshold? I mean, shouldn't it just be linear right through the origin? And keep in mind this, increasing the intensity of the light, that has no effect on the kinetic energy of the electrons. The only thing that changes the energy of the electrons is this: once you pass this magical threshold frequency, once your photons have more than this amount of magical energy here, E equals hf0, then you always get this photoelectric effect happening for larger and larger frequencies. And then it works linear. Then it goes how it should. It's just this weird thing, like, why is this here? Now above this or here, like I said, the electrons, the kinetic energy of the electrons is proportional to the frequency, right? So you have this, right? Yeah, E equals hf. So it's some sort of graph, and you could take the slope of this, and you'd end up probably with something relating to h. So this is how it goes, but this is really confusing. So along came a really clever guy by the name of Einstein. I'm sure you've heard of him. And he figured out the reason, among other things. He figured out, well, first of all, the energy of light is quantized. That means photons have energy that's a multiple of h. That's why we have that equation, E equals hf. Now we have electrons. This is his idea, was that the electrons must be trapped in the metal. And they're being held, they're being bound in the metal by some sort of energy. We call that energy the work function. And that's going to be measured in electron volts usually. It could be in joules. But basically, it's the energy needed to eject the electrons. So if you think about it, you've got these photons coming in with a certain energy, E equals hf. But if they don't have enough energy to overcome this work function, in other words, if they come in too low energy, like, like over here on this graph, like over here, those photons don't have enough energy to overcome this work function. And what is this work function? It's like this amount of energy that's holding those electrons in. So you have to have enough energy to basically force them to be released. So that's the brilliant thinking of it. He actually won the Nobel Prize for this. So what I think is interesting is that if the energy of the incoming photons is less than this phi here, this work function, it's not enough energy to eject the electrons or overcome the work function. So that's why no photoelectrons are seen. That explains the threshold frequency. And then you're given this really handy equation here. E max equals hf minus phi. Keep in mind the units here. Look, this right here, isn't that an energy which could be measured in electron volts? We have hf. Isn't that the energy of a photon? So yeah, so that's an energy measured in electron volts. And then we have this weird work function thing. But that's an energy measured in electron volts. So we have like energy equals energy minus energy. I hope that makes some sense here. So the interesting thing is this Emax, what is that? It's the maximum kinetic energy of these electrons. So these electrons that are shooting out of there, that's their maximum kinetic energy. You can use that to find their speed, I guess. H is still a constant. Remember, it's 6.63 times 10 to the minus 34. You can look it up. F0 is your frequency of the incoming light. So this HF could also be equal to HF0. That could be actually it. So let me actually just delete this one here. It doesn't have to be it doesn't have to be F0. It could just be F. So that's the frequency of the incoming light. So remember, in this E here, that's the energy of the photons coming in. This is the work function. This is the maximum kinetic energy of the electrons. So it's all written in energies. So now we have an example for you. We have photons, and they have an energy of 2.2 eV each. So each photon has that energy. So they're incident on a metal surface. And first of all, let's find the... Oh, God, what have I done? Oh, no. Undo, undo, undo. There we go. I think I was under the delete button there. So we want to calculate the frequency of this radiation. So what do we remember that? We want the frequency of these photons. Well, these photons have an energy 2.2 eV. We probably need that. Well, in order to do frequency, we're going to use the equation E equals HF. Does that make sense? We're going to do then F equals E over H. And we know H. H is 6.63 times 10 to the minus 34. You can look that up. But I need to know, what is the energy? I need this in joules. So what I'm going to do is I'm going to have to convert this energy. So 2.2 EV. I have to convert that to joules. And remember, we can do this little fraction trick here. I need something with EVs on the bottom in order to cancel out those top EVs. And then I know that there's 1.6 times 10 to the minus 19 coulombs. Not coulombs, sorry. Joules. In an EV. And remember again where that came from? That came because you know that 1 EV is 1 charge of an electron times 1 volt. And charge of an electron is 1.6 times 10 to the minus 19 coulombs. But coulomb times a volt turns out is a joule. So here we go, we get this. Let's actually figure that out. I guess that would help, huh? So 2.2 times 1.6 times 10 to the minus 19. That gives me a value of 3.52 times 10 to the minus 19 joules. Now I'm going to put that here then. So 3.52 times 10 to the minus 19 joules. Take that answer. Let me just make sure I did it right. Yeah. I'm going to take that answer and divide that by 6.63 times 10 to the minus 34. I should get a lot of numbers here. Oops. Yep. So I end up with the frequency is, and I'm allowed two significant figures. So 5.3 times 10 to the 14 hertz. Oops. That's not a hertz. That's a hertz. So there's your answer. That's a very high frequency, isn't it? It's a very large frequency. Now, let's do this one. Assuming the incoming photons have the same energy as above. So in other words, we're going to assume these photons have the same energy, which could be 2.2 eV, or if we feel like it, we could say 3.52 times 10 to the minus 19 joules. Either of these numbers will be the same. That'll be fine. Find the maximum speed of these emitted photoelectrons. And we're this time considering what's a surface of potassium, which is element number, what is that? Well, at least the element symbol is K, isn't it? But potassium. Now we're told the work function is this. So this is the important part. We know the work function is 1.5 eV. What do I do? Luckily, I have an easy equation. It's actually really easy. Look, E max is equal to HF minus phi. So let me just write that down. So that way, if I'm showing this to my examiner, I can show them I know what I'm doing. So E max equals HF minus phi. All right. Do I know HF? Do I know the energy of my photons in electron volts? May as well do it all in electron volts. Look. We can say the E max is going to be in electron volts. I can say HF. But in this case, HF, I can just say that's just 2.2 eV. That's our incoming photon energy in electron volts. The reason I'm doing that is because we're given the work function in electron volts, right? So we have this. This is our E max. So what's that? That's 0.7, isn't it? So I have my delta E max, I guess. Oh, I don't need a delta, actually. I'll just say so. My maximum kinetic energy, E max, is just 2.2 minus 1.5, which is 0.7 eV. And what do I do with that number? I probably need that. If I want to know the speed, do you see that I need to know that EK is half mv squared? So I'm going to need to know everything in sort of proper units. I don't need these electron volts here. So I'm going to try to get rid of the electron volts by, again, multiplying by 1.6 times 10 to the minus 19, because there's that many joules in one electron volt. Electron volts cancel out. I end up with 0.7 times 1.6 times 10 to the minus 19. And this is my answer here in joules. So it's 1.212 times 10 to the minus 19 joules. And now, of course, what do I use that for? Well, I know that 12 times 10 to the minus 19, that equals, because that's a kinetic energy. So that means I know that's equal to half mv squared. Therefore, V equals, let's see, it would be 2 times this. 1.12 times 10 to the minus 19. It'll be 2 times that, yeah. Divide that by the mass of an electron. What's that? Is that 9.1? Let me just look it up here. What's the mass of an electron? I think it's 9.1. Yeah. 9.11 times 10 to the minus 31 kilograms. And I'll take the square root of all of that. Let's do that on the calculator then. Figure that out. So 1.12 times 10 to the minus 19 times 2. Divide that by the mass of an electron. Let's hope we get this right here. At least we've done it right. So then I have this value right here. I have a V then, which is 4.9 times 10 to the power of 1, 2, 3, 4, 5. 4.9 times 10 to the 5 meters per second. Pretty fast. Remember, something like 10 to the 8, that's the speed of light. So these are electrons that are actually going pretty darn fast here. You can see how we can actually solve all this. So photoelectric effect does not have to be so bad. It does not have to be so scary for you. I'm going to talk to you about the Bohr and the Schrodinger model of the atom. By the way, I'm probably saying it wrong. I'm not German. So how do you say this one here? I think it's got the umlauts on it. I think they call it like Schrödinger, I think is what a German says. I can probably pronounce Bohr right, or at least close to it, because I live in Denmark and Niels Bohr was a Dane. So let's talk about the Bohr model of the atom. There's a lot of different ways of looking at the atom. His way, I mean, there's a lot of other things based on this, but the stuff you need for the IB is this, that the electrons in the hydrogen atom, they have stable orbits. So what that meant was, see, if you did the math before this atom, it would say that as they were just orbiting around, they should give off radiation, therefore their orbits should sort of degrade. His thing said, no, they can be stable, they can be happy where they are. No problem there. Next thing, this whole thing we've been talking about before, that the electrons can go up or down in orbit based on these quantized number of energy. So this could be this E equals HF. And of course they emit radiation when they go down. This is this whole idea about these energy levels. When they go up, then they go down, and they emit a photon. Right? That we know. Now the other thing he said was this, the angular momentum of the electrons, that's quantized in integer amounts of h over 2 pi. So what does this mean? This is actually an equation on your data booklet. I haven't seen them really use it much on exams, but I mean, hey, it's in the syllabus, they've added it, so I wouldn't be surprised if this shows up, at least in an easy way to explain it. I think what would help to know is this, when you talk about angular momentum, it's a little bit cheap because, you don't do so much of it in IB physics, but this is the angular momentum right here. This first part, this is the angular momentum. And if you're going to say that the angular momentum is quantized in integer amounts of h over 2 pi, what that means is it only comes in numbers of this. So you got h over 2 pi, and notice what n is. N is just an integer. That's why it's integer amounts. So for example, let's just say you have the angular momentum is equal to 1 times h over 2 pi. That's allowed. Or it could be 2 times h over 2 pi, or 3, or so on. So n is just these integers, positive 1 and higher. So we talk about these different things. This is the mass of the electron. That is measured in kilograms. You can look it up. What is it, 9.11, I think, times 10 to the minus 31 kilograms, something like that. Speed of the electron will be in meters per second. We have radius of the orbit. That should be in meters, I would guess. This is just an integer number, so they have no units, and h is just a constant. That's the one at 6.63 times 10 to the minus 34. Again, look it up. So this, I don't know what really they could ask you other than just, fill in N and M and maybe what's V or what's R or what's M or what's N. They won't ask you for H because H is known. But other than that, they could ask you one of these variables and not give you the other ones. So here we have orbital energy. This is another thing that came from the Bohr model of the atom. He was looking at this especially, this is for hydrogen, by the way. This is for hydrogen. So for the simplest atom, the nice simple one, he said that En, where N is just a subscript, it's just it's an integer. Again, it could be 1, 2, 3, 4. He just said the energy of the nth orbit, so the energy of this electron in this orbit, will be given by minus 13.6 divided by n squared. So for example, if you have n equals 1, then it's just minus 13.6 over n. By the way, so this over 1. Or if it's over 2, then it's 13.6 over 2 to the power of 2, which is 4. So you have 13.6 over 4. That's the next one, and so on. So En is the energy of the nth orbit, but it's important it's in electron volts. And maybe it's a good idea to just do this question here, so just to have a little bit of practice. This is an exam kind of question. So we have an electron in a hydrogen atom. It's excited up to the third orbital radius number. That means now it's at n equals 3. That makes any sense? Then it undergoes a transition down to the ground state. What does that mean? Ground state is n equals 1. Not 0, but 1. So now it goes from n equals 3 to n equals 1. What's the wavelength of that photon? Well, what we can do is we can find out what's E3. In other words, what's the energy of the third orbit? Let's see, it's minus 13.6 over 3 squared. Well, that's minus 13.6 over 9. Let me figure that out. So we have 13.6 over 9. So that gives me negative 1.51 electron volts. Okay, great. Let's do E1. What's that give me? Well, that's negative 13.6 again. Now we have to have like before. We divide that by 1 squared. And 1 squared is just 1, so that means it just gives me a value of negative 13.6 eV. So now we have E3 and E1. And I hope it makes sense. We have to do delta E. So that's just going to be these two subtracted. Right, so we just need to know the difference, right? So 13.6 minus 1.51. I'm just doing the absolute value here. We end up with what? 12.09 electron volts. So I think that's actually pretty interesting here. We've got this energy now in electron volts. Now, what do we do with this? If we want this wavelength, what can we do? We need a wavelength here. Do you remember what we can do for EE? This is the energy we're looking at in electron volts. We could first convert it to joules if we wanted to. So we can get rid of the electron volts. So that means we have 1.6 times 10 to the minus 19 joules for every electron volt. So let me try that. So I'll multiply my answer by 1.6 times 10 to the minus 19. Whoops. What did I do? Times, times 1.6. So my calculator is doing something really strange. There we go. So now I have my delta E in joules is 1.9 times 10 to the minus 18 joules. Why do I need that number? Well, because I want the wavelength. Remember, E equals HF. And if you remember your equations, remember C equals F lambda. That's your wave equation. If you want to get F by itself, you can say F equals C over lambda. So that means everywhere I see an F, I can write it with HC over lambda. And if I want to solve for lambda, fine, lambda equals, this would be HC divided by E. If I just move the lambda over and I move the HC, I move the E down. All right, so let's put in the numbers. 6.63 times 10 to the minus 34 times C, which is 3 times 10 to the 8. All that divided by the energy in joules, which is 1.9 times 10 to the minus 18. Let's try this out. I'm going to save that answer. So 6.63 times 10 to the minus 34. Whoops. Something wacky happened on my screen there. There we go. Times 3 times 10 to the 8. All that divided by my answer that I just got, right? So 1.9 times 10 to the minus 18. If I do this, I end up with a wavelength of let's say actually, times 10 to the minus 7 meters. What that means, this is 100 nanometers, you could say. So this right here is something that is probably not something we're going to measure with our eye, at least. We certainly won't see this. This is way beyond ultraviolet for the eye, so we won't notice this. But it's about 100 nanometers, or 1.0 times 10 to the minus 7. So something like this, that should help. Now, I want to talk to you very quickly about this Schrodinger model of the atom. His idea was really brilliant. He said, okay, we can't know everything in quantum mechanics, but let's write a wave function. They call it psi, this little sort of symbol like that, to represent everything you can know about your system. So what you basically do is put in all the stuff. It's almost like a big sort of mixing pot. You just sort of mix it all up, and then you end up with what you can do. It's a mathematical equation. I mean, there's this whole thing called the Schrodinger equation. It's a little bit complicated. It's beyond what we need for the IB. It's a great equation. I've taken a few classes and we played around with it a lot to try to find out what kind of solutions do you get, what does it do. And one of the things that it does that's useful, so by the way, the good news is you don't have to work with that equation because it's super gross, especially for IB level. But if you know this is the one thing you're supposed to know, that the probability of finding an electron in a small volume is equal to basically the amplitude of your wave function, which is what this is. So this is the amplitude of that psi here, squared times your small volume. Now, what does this really do? I mean, this is just an equation, right? I mean, you could be asked this. I've seen this show up a few times on exams. They ask you, like, what's the meaning of, psi squared? And you say, oh, it's the probability of finding something there. That's the most other thing they need you to know. The most important sort of result from quantum mechanics from all this stuff is that the universe is no longer sort of deterministic. In other words, it doesn't matter, even if you know all the physics and all the rules, you can't actually predict everything's going to happen. Turns out the universe is probabilistic. In other words, it's like there's just like rolling the dice. It turns out anything is possible. It just depends on if you observe it, then you force that thing to have happened. So that's actually related to it's called the Copenhagen interpretation. That's related to Bohr's idea of the atom. This idea that any possibility is possible, except when you actually observe it, then you force it to be just one thing. That sounds a little bit dodgy, and he got sort of a lot of flack from people about his cat. He just came up with this idea about a cat, about, you could devise some sort of experiment. You have a box and you can't see anything. You have this devised experiment that, could randomly, basically, through absolute random chance, kill a cat. Obviously, he didn't kill any real cats. People freak out because they haven't read it. So he didn't have anything against cats. That's why I like this. Schrodinger, wanted, dead, and alive. Because this is the whole idea, is that before you make the observation, all the states are possible. The cat could be dead in the box, that you can't see. The cat could be alive. It could be dead and alive. It turns out it could be in another universe. Who cares? But what happens is when you open up the box, you make an observation on the system, you force all the other probabilities to collapse to nothing, and you end up with the one result. Either the cat's dead or it's alive. That's why I love this very first picture here that I'd shown you. The Schrodinger plates. Look, they're both broken and not broken until you open the door. Do you notice? It looks like they're about, basically as soon as you open the door, everything's going to break. So I thought that's actually pretty brilliant. So quantum mechanics does lead to some really weird stuff. It leads to the fact that the universe seems to be probabilistic. It seems to be that it's just random chance. You just have to work out the probabilities of things happening, and then you figure out what's most likely going to happen. But weird things are possible, which I'll talk to you about in the next video. Heisenberg's uncertainty equation is one of my favorite equations. If you can have a favorite, it's mine. It's really deep, actually, what it ends up meaning. Even though the equation itself looks really, really simple, I'm going to just show you. Here's the equation, just delta x delta p greater than h over 4 pi. Who cares, right? It's what it means that just blows my mind. So I have this whole actually presentation. I do a whole TOK presentation actually about this. I actually call it quantum mechanics and the equation for free will. And this Heisenberg's uncertainty principle ends up being the equation for free will. I want to explain just very, very briefly the idea behind all this. And it stems from this idea, at least the result, that the act of observing or making a measurement actually alters the system. At least on if you're doing it on a very small scale, it can. So this is the idea. It came from a very, very simple concept. The idea that what is light? Is light a particle? Is it a wave? And there existed some experiments you can do, like, at first people thought it was a particle because, light can bounce off things, so reflection works. It can refract and slow down, so that worked. But then you do diffraction, something like this right here, where, you'd expect if light was a particle, wouldn't you expect that, if light was shining through these two openings here, and projected on the screen, wouldn't you expect that light should do something like this? These two sort of big dots. If light was a particle, it should do that. But it turns out if you have the right sort of conditions here with the right sizes of these openings compared to the wavelength of a light, you can end up with something like this. You end up with, you ever seen this sort of diffraction pattern here? This sort of thing right here where you see these different dots here like this. It's the spreading of light. And it turns out a particle can't do this. Only a wave can do this. So then everyone was happy, like, okay, got it. Light's a wave. We got it. We figured it out. You can go back and do the math. There's a Dutch guy named, we call him Huygens, but I think Dutch call him like Huygens, or I'm probably pronouncing it wrong. If you're Dutch, I'm sure you'll correct me. But But anyway, he had figured out the math back on all this stuff to figure out, okay, well, if light is a wave, then you can do the wave equations for reflection, refraction, everything works out. Great, light's a wave. But then along comes another experiment, this photoelectric effect, it turns out. If you do photoelectric effect, only light as a particle can do that. And then it becomes really confusing, like, what? You're telling me that this diffraction thing that I just showed you right here, like that means light has to be a wave, not a particle. Yes. Then you do this other experiment, this photoelectric effect, say light as a wave can't do this, only a particle could do this. Yes. So which is it? Is it a particle or is it a wave? That's why I love this thing right here. Light is a, if you read it carefully, it looks like a wave. And if you look at it really carefully, it looks like particle. Clever. I love this. So that's why it could be a wave, or it could be a, obviously like P, A, R, T. You get the idea. I, C, L, E. A particle. That's the idea behind, right? Yeah, it's supposed to be an R here. So particle. So which is it? What I love is that, a lot of these quantum mechanics bigwigs, they're basically saying, don't worry too much about what it is. Does it have to be a wave or a particle? Like, just let it be what it needs to be. Let it be whatever it wants to be. So you don't have to worry too much. Now, the interesting thing is this. They did this experiment, and it turns out something really interesting was happening. You could send not just light, you can send solid matter through this. So let's say we do the same experiment with this, 2 slits, for example. You can send, electrons, which we for sure knew weren't waves. Those are particles. We would shoot electrons through this, and it turns out electrons, under certain conditions, they can do this. So solid matter can do this. Like, what? You're telling me solid matter can act like a wave? Yep. It's this idea actually called the de Broglie hypothesis. This idea that light can actually, it has a wavelength. It can also have a momentum. And it turns out then it means that anything else with momentum can also have a wavelength. So they call this a wave-particle duality. So you can see, like, where am I? What's my momentum? Where am I? What are you worrying about? Am I a wave or a particle? Basically, it's this idea that waves can act like particles, particles can act like waves, so really strange stuff. And trust me, this is very weird. So then scientists at the time, this is early 1900s, they're trying to figure out, okay, what in the world is going on here? All our particles are waves, everything's a big mess. Of course, I'm paraphrasing immensely, but this is the basic idea. So what I think is so fascinating about this is this. They decided, all right, let's figure out, if these solid particles like electrons are acting like waves, that means they must be somehow like interfering with themselves. So they thought maybe this electron is like, maybe there's 2 electrons and some of those 2 electrons are interfering with themselves to make this wave sort of behavior. So they did something really clever. They thought, let's just fire 1 electron at a time. Just 1 electron, then another electron, and you wait. There's no way those electrons could then interfere with each other. And you still end up with this diffraction pattern. You're like, oh God, what? So then they thought, this is really clever. And they said, okay, let's try to find out which hole did the electron go through? Because if it's going to interfere with itself, which opening is it going through? So this is the amazing part. They do this experiment where they can detect which hole it went through. So I don't know, you have some sort of detector, maybe like a photomultiplier, something that anytime a photon or electron or something passes through here, it basically says a blip and says, I got it, it went through this hole. Turns out when you turn on that experiment and you do this sort of thing right here where you actually detect which hole it went through, then the electrons behave like this, like particles. When you don't care where they went through, in other words, when you're not looking at, you're basically not caring where they went through, you just let them do their thing, they do this. So it's like they're being watched, or at least they know they're being watched. Now, I saw this, what was it called? What the bleep do we know, I think, from YouTube? That is totally not what's going on. They add a lot more mystery to things. No, these electrons are not sentient. They don't know they're being watched. But isn't this strange, I think, is the important thing. So they figured out this, the act of observing. And I really do mean this observing, like making a measurement. If you're going to detect which hole it went through, it alters the situation completely. So people thought, oh God, maybe there's like sentient atoms and things. No. It's actually not nearly that complicated. It's really simple. Turns out Schrodinger helped us to figure it out. It's all about probabilities. The idea was this. Any probability is possible any possibility is possible when you haven't made an observation. You just let it be, right? You let them pass through whatever they want to. Anything is possible. They can pass through one hole, the other hole, or both. The dodgy part comes when you actually do make the measurement. When you actually measure and say, it for sure went here. Do you see that? That means there's no way it could have gone through the other one. So it's like you observe the system means you collapsed all the other possibilities. That's why then it will act like this. It's still really strange. I will absolutely give you that. Famously, someone said, was it Richard Feynman? I don't know, he had said this, I'm paraphrasing here, but he basically said, no one really knows about quantum mechanics, exactly how it works. Now, it doesn't mean it's not an important endeavor. It just means that there is a lot to figure out, and the universe is way weirder than we could have ever imagined. Turns out everything's about probabilities. Turns out anything is possible. This is really mental, but watch this. If I take my hand right here, and I just keep like tapping my finger at my hand, there's a probability, not zero, that my atoms will decide to go just through my hand. It won't make a hole. They'll just like end up at the other end. It's called quantum tunneling. You're like, what? Good news, the probabilities are very, very small. That's why good news, solids are still solids. But on a very, very small scale, we say quantum mechanical scale, which means extremely small things. Let's say you fire electrons at a thin thing, and those electrons, there's a probability that one of those electrons might pass through that object. This quantum tunneling. And you can actually do the math and figure out the probabilities through this wave equation of Schrodinger's. And you can actually calculate then what's the probability of this happening. And you can say, looks like I should have, I don't know, this many per hour happening. And then you actually do the experiment and it happens. This really is possible. So weird stuff happens, stuff that we really have trouble wrapping our brains around. But the universe is really weird. But the one thing that seems to be is it's all about probabilities and about measuring. Measuring, it turns out, seems to alter it. So now comes this. Planck figured out the smallest interaction you can have. And you might say, well, I'm going to make the tiniest measure. I'm just going to look at it and just going to... Well, he figured out the smallest little you could have. He said it's 6.63 times 10 to the minus 34. And I think it's joule seconds, if I remember correctly. So this tells you this is the smallest interaction you can have, which is really small, but you can't have smaller than that. So Heisenberg, the clever guy that he was, he figured out, let's use this idea and let's work out how it works. And he figured out this, that delta x, delta p is greater than or equal to h over 4 pi. This is the uncertainty equation. This is actually, I would call it the equation for free will even, you could say. Now, what this means is this. You've got the uncertainty on position, which means when you actually make a measurement of position, you have an uncertainty on it. You have some sort of fuzziness in your measurement. That's delta x. Then you have delta p, which is the uncertainty on momentum. Remember, momentum contains a velocity term, so it's like saying speed. So you have, your uncertainty on position, you have your uncertainty on the speed. And have to be greater than some value. And what this means is really fundamental. It's powerful. What it means is that if you know something's position really, really well and accurately, that means that your delta x gets really, really small. In order for this inequality to hold, delta p has to go bigger. Which means the better you know, that's why I write it down here, the better you know an electron's position, right? So if you know an electron's position, so delta x is really, really small, the worse you know the speed, because delta p is really large. And vice versa. The problem is there's a fundamental limit to the universe in what you can measure. You can't know both. Which is why I would say it's the equation for free will, because it shows that you can't live in a deterministic universe where you can calculate everything. Because now it becomes very fuzzy. It's all about probabilities. You can't know anything for sure. By the way, there's also a version with energies and times. Now comes, and I like this t-shirt then, right? This I'm uncertain about quantum mechanics. See, it's about uncertainty. And I think now we can actually explain one of my favorite jokes. Are you ready? Now that you know about Heisenberg's uncertainty principle. It's really, really short. It's really, really simple. You might have heard it before, but if not, I think you're going to like it. Heisenberg's driving in his car. He gets pulled over for speeding. The officer says, any idea how fast you were going? He says, no, but I know exactly where I am. Yes. Because of delta P and okay. Anyway, one way I would like to explain it to you maybe with this idea of uncertainty is just like with just looking at pictures of motorcycles at some point. And I remember thinking, I don't know why, because I don't ride a motorcycle. I'm too scared. But if you look at this reminds me a little bit about uncertainty. So watch this. If you see a picture like this of a motorcycle, someone's actually sort of, taking a picture, a snapshot as they're sort of panning, as they're sort of moving the camera along. What this ends up doing is this. It tells you you can have an idea about the person's speed here. Does that make sense? Because the blurriness of the background tells you something about the velocity. But do you notice though, if that's the case, you have no idea about this guy's position. I'm assuming it's a guy. I don't see hair sticking out. Of course, girls can have short hair. I don't know. Assuming this person's speed. You can tell the speed somewhat from the blurriness of the picture. But by that, the more blurry the picture gets, the background, you don't really know this person's position. So it's kind of like this analogy here. Whereas, by contrast, this kind of picture here, you've taken a very short exposure time picture where you can really see the background. Can you see here? You can tell this person's position. They're right in front of this red thingy here, and this grass is right there on this corner. You can know this person's position pretty accurately. Do you see though here, you have no real way of telling, just from this picture, this person's velocity. It's like, now that you know the position really, really well, you don't really know this person's speed. You're assuming they're going fast enough to stay upright. I mean, maybe this person's just taking a nap and just sort of leaning like this, So I'm just trying to say this is a way to try to help you to understand this idea here that we can know something's position really well, or we can know its momentum really well. In other words, delta x can get really, really small if we know it well, but we can't know both. The better you know one, the worse the other one gets. There's a fundamental limit to measurement in the universe. Awesome. I'm going to show you some nuclear physics that adds to what we've done in the SL part. First of all, we have this equation. Well, I like this from Big Bang Theory. What did the nuclear physicist have for lunch? Fission chips. And so a nuclear physicist, he actually had a boat, and it was called Gone Fission. Get it? So there is a nuclear radius. This is an equation that's in your data booklet. I haven't seen it show up many times on exams, so I won't spend much time on it, but it says that the nuclear radius R is of an atomic mass number A. Remember the atomic mass number, that's the number of nucleons. Remember that when we write an element, let's say, something like helium, let's say. The atomic mass number would be this top number. That's the number of protons plus neutrons. In this case here, it's got 2 protons. So because this is 4, we know that 2 protons plus 2 neutrons is the way to get 4. Anyway, you can basically figure out the nuclear radius. This is always in meters, of course. And they'll be very, very small numbers. Expect really tiny numbers, okay? And that's just the equation. Let's go on to something maybe that's more likely to show up on exams. First of all, just a reminder of this curve here. This, if we have the number of atoms, let's say, or it could be a mass. It could also be activity, by the way. Activity could also be this. Remember this curve? It's exponential. It goes something like, I'm not really drawing it that well, but there you go. We start off at 100% of something. Then there exists a time where you have 50%, right? That's this value right here. We call that T1 half. That's the time to get half of the original amount or mass or activity. Then, because I'm trying to go quickly so I can spend the time on the things that do show up most on exams, let's just remind ourselves about alpha decay and how it works. Remember how alpha goes? Alpha decay means you end up just adding, you always just add a helium-4. That's what it means to have alpha decay. And remember, if you have beta decay, there's 2 types. There's, whoops, I didn't write that very well. There's something called beta minus, which is an electron. But every time you get beta decay, don't forget you also get a little electron neutrino. And this gives you have the antineutrino. Because from particle physics, you need a particle and you need an antiparticle. We have the other kind of beta decay, which is a positron beta decay, it's called. And because this is an antiparticle of the electron, then you're okay with just the electron neutrino, the normal kind. So I'm just trying to remind you what happens with these kind of decays. Now, let's go more detailed about this decay curve. I think that's the really important one here. So decay is exponential. I want to go into more detail because we have this equation here for n, and it's an exponential. I mean, notice this curve is exponentially decreasing, right? So because of that, in physics HL, we actually break in and do some details on this equation. So we have n equals n0 e to the minus lambda t. And I want to point out one thing really important. Lambda is not the wavelength. You might think so because you're used to only seeing lambda being the wavelength. You might have thought that was one of the only safe Greek letters that always means the same thing, but nope, it does not equal the wavelength. In nuclear physics, it's called a decay constant. And that's the probability of a decay happening in a given time. It's measured in like seconds to the minus 1, or you can say, years to the minus 1. It basically doesn't matter too much, but some unit of time, like 1 over time. Now this equation, the way it works is this. You have n, which is your initial mass, but you can also write it for activity. In other words, we can write the same equation. Instead of n, we can say A equals A0 e to the minus lambda t. That's allowed. Okay, so the activity works the same way. And remember what activity is? Activity is decays per second, which is measured in BQ, we call them. These are becquerels. Okay, so named after Becquerel, oddly enough. So we have something else called activity. So we can have either the number of atoms, for example here, or we can have the mass, or we can have the activity. They all work in the same way. And we have this nice little one right here that relates activity with the initial mass. You just have to throw in this lambda, this decay constant again. Now, what's interesting is that you should really know how to do this derivation of the decay constant and the half-life equation, because this is something I think it's really, really important to know. Also because this is not in your data booklet. I can't find it, at least, unless it's in a secret place. I can't find it. So we have this equation you should be able to come up with to relate lambda, this decay constant, with the half-life. And I want to just briefly go over with you how we actually do that derivation. It's good news, it's not hard. So how do we do the derivation? Well, we start off by saying we're going to use this equation, n equals n0, except we're going to define something. We're going to say at t equals t1 half. In other words, when we are at the half-life, can you tell me or think about what do you think n is compared to n0? In other words, what do you think your final mass is compared to your initial mass? And I hope it makes sense to you that n is going to be equal to n0 over 2. Why is it over 2? Because that's the definition of half-life. It's the time where you have half the original amount or activity. So because of that, then that's what we put in here, and that's all we need to do in order to solve this. Now we just need to do some math. So the physics is over, now it's just a math question. Let's see if we can do it. So instead of n, I write in n0 over 2, so watch carefully. So n0 over 2 equals n0, that's the equation here, e to the minus lambda. Instead of t, I put in t1 half. All right, well, good news, my n0s can cancel out because I can divide them both and you end up with 1. So now I have 1 half. I'm going to show you every step, okay? So 1 half equals e to the minus lambda t1 half. Now, how do I get rid of an e? You have to think about what's the opposite function to exponential function. And you might remember this, or maybe not, I don't know, but you take the natural log of both sides. So you do natural log of 1 over 2 equals the natural log of e to the power of, well, let me just cancel that out. Turns out natural log of e, they undo each other. So it's like this top part, this minus lambda t1 half, sort of the e disappears, so they just sort of falls to the bottom. So it's like minus lambda t1 half. Now you got to remember your rules of logs. Remember this from math class maybe? That turns out the natural log of 1 over 2 is the same thing as saying natural log of 1 minus natural log of 2. That equals minus lambda t1 half. And then you got to think about what's a natural log of 1. Think about that. We can do it. That's just a log base e of 1. I like to write sort of equals x, so I don't know what to do here. And then I do this to the power of this equals this. So I know that e to the power of what equals 1. And the only thing I can bring e to the power of to get 1 is 0. If I make e to the power of 0, I get 1. Therefore, I know that this answer is 0. Therefore, I know this thing right here is 0. Because of that, I have minus ln2 equals minus lambda t1 half. Do you notice what happens with the minuses? They're going to disappear, or they're going to become pluses. All right. So basically, do you notice now I have, let's say I can solve for t1 half, couldn't I? I can say t1 half equals, let's see here, it could be ln2, natural log of 2, divided by lambda. And this is the equation you need to use. Of course, you can do the other version. You can say lambda equals ln2 over t1 half. So this is super important, but you see how you can do the derivation? It may not be very fun, but if you tried it once or twice, you'll be fine. Now comes an example. Because by the way, you are fully expected in physics HL to be able to solve for t. They do expect you to be able to get to t here. In SL kind of questions, they're always really simple, where it's always a multiple of the half-life, so it's really easy. In this case, nope, it could be any time. Here's an example from an exam. So it's an example. Sorry, that's too bad. So we have a sample of cesium-134. So let's maybe write that down right away before I forget. So it's cesium-134. And I don't know which atomic number is. We'll just leave it. Has initial activity of this number. So this right here, this is A0. A0 equals 4.7 times 10 to the 8 becquerel. I know its half-life is 2.1 years. All right, so I know T1 half is 2.1 years. And you can leave it at years, actually. You're allowed to do that. Now, what's a decay constant? That's lambda. So remember we have this equation here. We have T1 half equals ln2 over lambda. So you can see I can also say then that lambda, I guess if I multiply both sides by lambda, I have lambda equals ln2 over T1 half. So I'm going to put that in. Lambda is ln of 2 over T1 half. Let me calculate that. It's ln2 over my half-life, which is 2.1 years. And notice my units, I'm going to get lambda is something over years. So I'm going to do natural log of 2. I'm going to divide that answer by 2.1. I end up with lambda is 0. I'll do two significant figures, so 0.33. And I can say years to the minus 1. All right, that's my decay constant. That tells me the probability of a decay happening per year. In this case here, it's not very big. Well, it's actually fairly big. I guess it's 33% in a given year. I guess it's not really much. Let's calculate the time in years it takes for the activity to drop to this amount of becquerels here. This is, let's figure that out. So here, if we want activity, we can do this equation for activity. I showed you it. It was this one here. A equals A0 e to the minus lambda t. So here I want to solve for t, but I got to put in what I know here. I'm given, let's put it in purple maybe, A, the final activity is this 1.7 times 10 to the 7. That's becquerels. That's the final activity. The initial activity we're given is 4.7 times 10 to the 8 e to the power of minus, and here we put in 0.33. Now this is per year, and I'm going to multiply that by the time in years. So the good news is it'll all work out really nicely, I think. We just got to divide these two numbers. So I'm going to do 1.7 times 10 to the 7 divided by this just to figure out what answer I get here. So that equals this right here. So let's do this. So 1.7 times 10 to the 7. Take that answer, divide it by 4.7 times 10 to the 8. I end up with this number here, 0.03617, something like that, equals e to the whatever. Now what do I do to solve this? Remember I do ln of this answer. That equals minus 0.33t. So I'm going to do that. So I'm going to do ln of this answer. So ln answer. I get some number. And I'm going to take that and divide it by t. See that? So t is going to equal, I'm going to get some number here. So do you see I would do ln of this answer here. I divide that by negative 0.33. I end up with an answer of t equals 10.059. Now I'm allowed two significant figures, aren't I? I've got 4.7, 2.1. Yeah, so I can just say then t equals just 10, I guess, years. So this will take you about 10 years to have an activity go from 4.7 times 10 to the 8 decays per second down to 1.7 times 10 to the 7 decays per second. So this is sort of what it tells you here. I think this is really important because we practiced how to do this by solving for t. So this is how you can deal with these kinds of questions, and I hope you found that helpful.